Good.
Okay, very good.
And
So let's see. Do we have echo still?
hello. I think it's fine now.
It's fine.
Yeah.
잘 되는 것 같은데.
Yeah. Yeah. It's okay.
Do you see my? You don't see my screen.
Yes, we can see your screen.
Which screen do you see?
The blackboard one.
Okay, good.
Can I request one thing? So after your talk and discussion, can you have a kind of 10-minute informal discussion with the students?
10 minutes before what?
Informal discussion with the students. So I think some of the students, they don't want to be recorded probably. So no?
Oh, they don't want to be recorded?
I don't know, but just in case, they can come to the front and ask us some question. Really? Yeah, yeah. That's. I mean, they are shy, so informal discussion would be encouraging.
Okay. Why do I have two videos there on?
Sorry.
I see two videos of me.
Two videos.
I mean, I have also here. So this is supposed to be my screen, but not my video. Let's see. How do I turn this off? Let's see. I'm trying to see if I can get rid of this. That goes away. Okay, that's better now.
그러면 students are still coming, so we will probably start after 5 minutes. Is it okay for you?
Perfectly fine. Yes.
Okay, thank you. Okay, hello everyone. So we will start today's program. So first speaker is Professor Kumnum Bafar. He will give us his second lecture on the swampland program. Yes, please.
Thank you. I'm very impressed with the stamina of the students here at Sunday at 9 a.m. there or something. It's impressive. So anyhow, I'm going to give the second lecture on the topic of string landscape and the swampland. Today, I'm going to introduce two particular criteria for the swampland. One is the weak gravity conjecture, and the other one is the distance or duality conjecture. So if you consider a U1 gauge theory,
Kumnum, are you writing? Oh, yeah, we can see you.
if you consider a U1 gauge theory and couple it to gravity, suppose it's coupled to gravity, we already know that there are charged states. As we discussed last time, the completeness of spectrum tells you that all charges appear. In fact, we know a bit more. You could ask, what is the relation between the mass and the charge of the states? Well, we don't know a priori what it could be, but we know that for large enough masses, we have a relation because we know that they can form black holes which are charged. And then there's a restriction for that, and that is when we know that M should be bigger than or equal to Q. Otherwise, we get naked singularity in the Einstein's solutions to Einstein's equation. In other words, we have a restriction that M should be bigger than or equal to Q. The line M equal to Q is the extreme odd case. So these are facts from solving Einstein's equation, and in principle, what this means is that there are states in the theory which are related to the black hole entropy, which correspond to states here occupied in this region where M is bigger than or equal to Q. Now, we don't necessarily trust this. We don't necessarily trust this for small m because the quantum gravity is not trustable if the mass of the black hole is Planckian, for example. We need it to be big enough. So if m is big enough, it would be trustable. And so we know that for large values of mass, at least, this should be trustable. So in principle, you can, and also large charges. So in some sense, you have to take a region sufficiently higher up. This region we can kind of trust. Now, the question is, how much do we trust the structure of this external black hole, and what can we learn from it? So if you look at black holes, the black holes are can be viewed as fundamental states of the theory, and so if you have a mass and a charge state, mass m, charge q, and consider another copy of the same thing, they will have attraction force and repulsion force. The attraction by the gravity and the repulsion by the electric force. So the repulsion will be proportional to q squared, and the gravitational attraction will be proportional to m squared. So if m is of order of q, then they will cancel each other. But in general, we would like to know if there is any relation between these masses and charges and so on. In the extreme case, they are equal. Now, on the other hand, we do not know what happens for small mass and small charge. So m and q small, we don't know what is going to happen because we cannot describe it using black holes. So we don't have much information for small m and q. So here I want to argue that one fact about black holes strongly suggests some relation for small m and small q, and that's what I want to explain. Start with a black hole with mass equals to q, And we're assuming that this state, this black hole is not supersymmetric, even though it's extremal. So we expect it to decay. We expect it to decay, even though we don't have a general proof. In all the cases that we know, when you have a black hole, it will decay. And the only cases where it doesn't decay are when we have supersymmetry protecting it. So let me assume we're just in the generic situation where the black hole decays, even though it's extremal. So if it's decaying, it's going to emit, let's say, a particle of charge Q and mass m. And when it does that, the mass of the black hole will be reduced by minus m and the charge by minus q. And so they're not anymore equal. In other words, you have m minus m on the one hand and q minus q on the other hand for the leftover black hole. But now the black hole has a relation that this should be bigger than or equal by the condition that it's not a naked singularity. On the other hand, m was equal to q. So therefore, we learned that the m is less than or equal to q. In other words, even though for the for the macroscopic black hole, we have a relation m is bigger than or equal to q, the condition that it's allowed to decay, it tells you that for elementary excitations, small mass and small charge, which corresponds to emitting, which gives the decay channel for the black hole, it satisfies the opposite inequality. The mass is less than or equal to q. So for elementary light objects, therefore, we expect the gravitational force, which goes as m squared, is less than or equal to q squared. In other words, if you have electric charges for the fundamental fields in your theory, we would expect that the gravity is the weakest of the forces. If you have a bunch of U1s, it's going to be weaker than all of them. So this leads us to the conjecture, which is called the weak gravity conjecture. So the weak gravity conjecture basically tells you that the mass of the black hole, mass of the elementary states, there exists elementary states which are charged for which the mass is less than or equal to its charge. This is the weak gravity conjecture. Now, you might ask, which charge are we taking? Of course, Q is a multiple of elementary charge units, n times some basic unit. And the weak gravity conjecture says that this is saturated. This is true at least for some n of order 1. It doesn't have to be the fundamental minimal charge. It could be, and there are examples in string theory, for which there is the fundamental unit does not satisfy this relation, but maybe the n is 2 or n is 3 or some larger value of n satisfies it. But it's not arbitrarily large, it's a bounded number. We don't have an exact upper bound, but we expect that for each dimension, there's an upper bound for what n can be. So basically means that for some fundamental field, by that fundamental, I mean basically light charge, small charge, there would be some state whose mass is less than or equal to that charge. And that means that the gravitational attraction between them is smaller than electrical repulsion. Now, this in particular means that the curve that we drew was not quite right. So let me just draw it again. So we have M and Q, and we had drawn this line saying that this is the way we expect the states to be for black holes. But black holes are nothing but elementary excitation, are representative of the elementary excitation of the theory. And so if we are saying that there are some states whose mass is less than or equal to charge, that means there must be a deviation from this line. And in fact, we expect this line, the extreme case, to go down under it. So we expect the states to be, could be some states which satisfies m less than or equal to q. After all, if we had the exact formula for the black hole entropy, it would have told us that there are some black holes because of mass less than q, because after all, black holes are nothing but excitations of the theory, and morally at least, even the fundamental states should be viewed as microscopic black holes. And therefore, to accommodate this relation, this curve should change. For this relation to change, that means the Einstein's equations should get modified. So in other words, if you start with the Lagrangian, which is of the form r plus f squared, we expect there to be corrections. And the corrections of the type that there'll be higher derivative terms, but the first relevant derivative terms, let's say for the 4D black hole that we're talking about, would be of the form a f squared squared plus, plus b w the Weyl tensor times f mu nu f alpha beta. So it turns out by
there is a question in the Zoom. Sorry.
There's a what?
Question in Zoom.
Okay.
Yeah. So the question was, some people argument that this argument applies to the particles that come out from the extremal black hole, but why can the conclusion be extended to all the particles that exist in nature?
So first of all, we are saying that the black hole can decay. And when the black hole decays, it decays by all the particles. Secondly, we are not saying that this is true for all particles. We are saying that there are some particles which have that property, because black hole also emits particles which are not charged at all. So if it emits, for example, photon, the mass of the photon is bigger than its charge. So we never said that mass is less than or equal to charge for every elementary state. That's in fact false. It's falsified by graviton, by photon, by many particles. We are saying the opposite. We are saying there are some states which are charged, and for those, m is less than or equal to q, and not for all of those q's either, only for specific ones, for the ones which are order 1 numbers in terms of the elementary excitations.
Thank you.
So, yes. So let me go back then to draw it, the extremality curve. So we said that the relation between m and q, to avoid a naked singularity, starting from r plus f squared gives you this region. But if we have corrections a and b, it turns out that this extremality relation gets changed to a lower curve. And this goes down if, and only if, in this case, 4a minus b is positive. So that means that the higher derivative corrections are crucial in figuring out whether or not this curve goes down or not. So this is basically, this weak gravity conjecture tells you, makes a prediction about the corrections, so higher derivative corrections to the Einstein's equation coupled to Maxwell theory. Now, in the cases that we deal with in string theory, this has been checked in a number of examples, and it satisfied these relations. So it's not obvious that it had to be, but that means there are higher derivative terms which satisfy this relation, and it's true. So let me actually give you an example for the weak gravity conjecture motivated from string construction, so you at least see one example, concrete example of this. But before I do that, I want to draw attention to one fact that we said the weak gravity conjecture says m is less than or equal to q, but it also allows m to be equal to q. Now, for m to be equal to q, we think this is an extremal condition, and this is satisfied for BPS states for supersymmetric theories. So supersymmetric BPS states. So there is an equality is possible, but otherwise there's going to be an inequality in that case. So the strong version of the weak gravity conjecture says that m is always less than q unless it is supersymmetric BPS. This is a strengthening of this conjecture. That you should expect there that the elementary excitation is always lighter than the charge, and the only case which equality is saturated is for supersymmetric theories. We have plenty of these examples in string theory, of course, for which m is equal to q. But I want to give you now some examples where we see both this behavior, m is equal to q, and m is less than q, for non-supersymmetric states. Notice that when I talk about non-supersymmetric states, I might be talking about them in the context of a supersymmetric theory. In other words, the theory could be supersymmetric, but the state I'm looking at is not preserving any supersymmetries. It's not the BPS supersymmetric state. So let me give a concrete example. Consider hydraulic strings. Compactified on a d-dimensional torus. Then the equation of state for masses in some normalization satisfies this relation. So you have winding and momentum modes, which can be captured by Narayan lattices, which satisfy the relation in terms of the oscillation numbers left and right in this form, where P left and P right and P left is the Narayan lattice, elements of Narayan lattice. Now, if NR is 0, if the right oscillator is 0, in other words, if you're in the ground state of the supersymmetric theory on the, in terms of the excitations, this can be a BPS supersymmetric state. In this case, as you see from this relation, M is equal to P. And this is an example of the BPS states, which satisfies M equals to Q. The analog of this case, you have many U1s, and this is the analog of the Q that I was mentioning before for the BPS states. So this relation is a statement of a BPS saturation of the state, and it's satisfied by these states. Notice that from the condition that n right is 0, it follows that 1/2 p right squared minus 1/2 p left squared is equal to n left minus 1. In other words, the half of p right squared minus p left squared is greater than or equal to minus 1 because n left is 0 or positive. So that means that it's not true that for every p left and p right, you can form a BPS state. In fact, if p right squared minus p left squared is less than minus 1, then they cannot be a BPS state. In such a case, the best we can do is to, instead of having n right to be 0, we can take n left to be 0 to get the minimal mass. So let's write that relation. So again, let me write the relation on this again. So we have a relation of this form. And now, since p right squared minus p left squared is less than minus 1, we set n right to 0. And once we do that, I meant n left to 0. That's the supersymmetric one was n right to 0, but now we take n left to be 0, and we get masses, which is equal to p left squared minus 1. But now you see that m is less than absolute value of p left because of this minus 1. In other words, this is satisfying the weak gravity conjecture in the same form that we expected, namely in the form that's an inequality. The mass is lighter than the charge, than the effective charge, which in this case is p left. Are there any questions? Yes.
Is there any, it might be a naive question, is there any way of understanding this asymmetry between the left and the right ones? That I have a special minus 1 sitting on one of the equations?
Between the left and the right one, you said?
Yeah.
Well, the right side is the supersymmetric side. Remember, hydraulic string enjoys supersymmetry only on one side, on the right movers.
I see.
So that's the asymmetries because of that for hydraulic string. And that's why there's a tachyon on the left movers.
I see. Okay, thank you.
You're welcome. Any other questions? Okay. Now, this weak gravity conjecture has extensions to higher dimensional objects. So here I was talking about particles, but you can actually extend it instead of just the point to higher dimensional membranes. So I will basically, what the conclusion was that you have gravitational attraction, but the repulsion always wins. So therefore, if you have particles, the gravitational attraction wins, loses to repulsion. And for the higher dimensional objects, the same thing. Namely, we expect that the gravitational attraction between extended objects, branes, if you set them, let's say, parallel to each other, would be smaller than the repulsion that they experience because they have the same charge. They would be equal if and only if they are BPS states. So for example, for the D branes, which are parallel to each other, those exactly cancel out and they will be exactly, there's no force condition between them. The attractive force and the repulsion cancel each other out. Now, this has dramatic consequences, this idea, for non-supersymmetric ADS. So let me explain that. So in fact, I want to argue that a non-supersymmetric ADS is unstable. By that I mean, so I will not be able to prove it in full generality, but I will motivate why this is actually a reasonable thing to expect. How do we get ADS in the context of string theory? Well, we put branes parallel to each other, and we take the near horizon geometry to go to the dual conformal theory. And the most well-studied cases are the supersymmetric cases, but in principle, we can consider non-supersymmetric collection of branes next to each other and ask the same question. And the same way we will get presumably a non-supersymmetric ADS as a dual. Except if you try to get parallel branes which are non-supersymmetric on top of each other, in the non-supersymmetric case, as we just argued, from the weak gravity conjecture, we expect the repulsion, gravitational attraction cannot win over the electric repulsion between these branes because it's weaker. And what that means is that this is going to fly apart. In other words, it's unstable. So we are making a very simple prediction that non-supersymmetric ADS cannot be stable from the weak gravity conjecture in the strong version of it, which is it's saturated if and only if it's supersymmetric. Now, this turns out to be consistent with all the examples we know in the context of string theory. Namely, whenever you construct non-supersymmetric ADS, you always find the decay mechanism, and it's unstable. For example, you can start with a supersymmetric ADS, like parallel D branes, and you can quotient out by some orbifold symmetries which break supersymmetry completely. And each time you do that, you find a decay mechanism. So again, consistent with this picture. Now, there is interesting predictions that this makes, which has to do just with pure gravity, and that's what one aspect of which is rather surprising, which was pointed out by Santos and Horowitz. So let me explain how that goes. Suppose you could just consider Einstein theory coupled to Maxwell. Just that, nothing else. Let's just assume such a theory existed. They studied this theory in a certain context, like ADS, and they found that if you consider a initial condition with certain initial condition and evolve it, after some time you get a singularity. And it turns out that it's not inside the event horizon. In other words, it's a naked singularity. In other words, you start with no singularity, you evolve the system, and you get a naked singularity. It violates the Penrose's conjecture that you should not have such a situation, that cosmic censorship, namely every singularity that you encounter, should be inside the horizon. Well, one answer to this might be that yes, that's the way it is. The conjecture of Penrose is incorrect, that these configurations arise. But the fact that naked singularities want to be hidden around the inside the horizon seems to be a very natural thing from various other examples. So could it be that this can be rescued in this case? It turns out that the weak gravity conjecture automatically resolves this issue. So what happens is that the way that they got these singularities, that the system evolves and the electrical field become very strong in these configurations that they had, and that leads to singularities. That's the mechanism they got singularities when you evolve it in time. However, there are a few things which are being ignored in this description. First of all, we know that because of completeness hypothesis or completeness conjecture we discussed last time, there must be charged states in this theory. Secondly, if there are charged states, and if you do have electrical field, you do pair create, for example, these charged states from vacuum. Now, of course, if these states are very massive, it will not be produced that much. But weak gravity conjecture tells you they cannot be too heavy. The mass is less than their charge. Mass or less than or equal to charge. So if you have enough electrical field, then you can indeed produce them. Now, you can check whether or not this will resolve this problem that they got, and indeed it does. It turns out precisely, if you assume that there is a particle whose mass is less than or equal to charge, as soon as the electrical field is strong enough to want to lead to singularity, it gets screened by the pair creation of these charged states. It basically gets rid of decreases the electrical field. And so therefore it avoids the naked singularity. So the weak gravity conjecture resolves the inconsistency, resolves the problem with cosmic censorship. So that's quite amusing because we didn't put this by hand. It's just a consequence of it. This is the kind of thing that gives us more confidence in this conjecture, that the ideas are connected with many other features of quantum gravity or gravity itself that we didn't put in by hand and kind of comes out. You see, here it's quite amusing. I'm using completeness hypothesis and the weak gravity conjecture to resolve the cosmic censorship. So you see how they kind of play together, the interplay between all these ideas. So that's how we can become more confident about them. One more feature about the weak gravity conjecture is that the weak gravity conjecture is the strengthening of the statement that there is no global symmetry. So, for example, suppose you have a U1 with some charge G or coupling G. If G goes to 0, this is going to be highly, basically similar to the case of a global symmetry. If you have no interaction between them, then you can basically not see any effect, which is different from a global symmetry. And therefore, you could call this theory a global symmetry. Weak gravity conjecture says that if you have some particle of mass m, you cannot take G to 0 because m should be less than G. You cannot take G arbitrarily to 0. And so this is an interesting way to say that there's an obstruction to take the make the gauge theory become global symmetry. The gauge symmetry remains a gauge symmetry, and this gives you a bound of what prevents it from happening. There are other extensions of the weak gravity conjecture, which is.
Can I ask a question?
Yes.
Can the weak gravity particle that we are discussing be massless? In which case G can be sent to 0?
Well, in principle, it can be.
if that's the particle, then G can be sent to 0, maybe?
Yes, but so I'm not, so indeed, if you view M and G as independent, sorry, if you view M and G as dependent, that's an alternative that it could happen. I'm saying something different. I'm saying suppose you start with a theory with a fixed particle masses, and then rescale, try to take G to 0 in that limit.
Okay.
That would be the thing that would be a problem.
Okay. Okay.
So let me say it in a different way. If you take M to be 0 to begin with, and you want to take G to 0, the weak gravity doesn't say anything.
Oh, okay.
But then you're having massless particles which are charged, global charge. And massless particles which are global charge has a problem with the black hole evaporation very, very trivially, because they don't, there's the same argument I was mentioning before. But at any rate, my point here was not to talk about changing both of them, but basically fixing a mass state and trying to take G to 0. That would be a problem. So in other words, this would say that you cannot have a global symmetry with any massive particle. That's what that means.
Okay, thank you very much.
Yeah. But there are more we can say. So in the context of ADS, in the context of de Sitter, lambda cosmological constant is positive. The size of the black hole cannot be too big. So in other words, when I was drawing the mass versus charge, I was drawing arbitrarily large mass. Mass goes like radius. But the radius cannot be bigger than the Hubble. And the Hubble h squared is lambda. So there's a maximum radius, which is given by the, lambda to minus 1/2, I mean the Hubble, h to minus 1. So you cannot make it bigger than the Hubble scale. So the maximal size you can have is lambda to the minus 1/2. So that means that the black hole cannot get too big and it has to stop somewhere. And indeed, it turns out that the structure of a black hole is different from the de Sitter case compared to the regular case. It comes to a stop, the biggest size, and that's what's called the Nari black hole. And the other region is something like this. So there's a region of allowed ones, which are now truncated like this, where the two other regions that we had, now we have two regions with naked singularity. One is lower part and one is the upper part. So the allowed region is now different from the previous one. Now, if you have a state here, the black hole here, if it decays in a direction to lead to naked singularity, you're in trouble. Now, it turns out that if you have massive state with charge, and the relation if M is smaller than square root of HQ, then what you can do is that you can emit such particles. The mass doesn't change much compared to the Q, and the slope of this line is such that you will not go down in this direction. In other words, instead of staying on this line, you actually deviate from it. And you because the mass doesn't change fast enough, it doesn't decrease fast enough, and you can get rid of more charge compared to the mass. And that will give you a problem. So this will tell you that there's going to be an inequality in the opposite direction for this to work. In other words, we want that M to be bigger than or equal to square root of H times Q. I didn't do the analysis to explain to you why this is the case, but one can do the analysis. And one gets an inequality in the form that even though that M is less than or equal to Q, it also has to have an upper bound. It has a lower bound given by square root of H, which is lambda to the 1/4 times square root of Q. So there's the two-sided inequality now that the mass of charged fundamental states, at least there are such states for which there are bounds on both sides. It's bounded upper by Q, but lower by square root of Q times the value of the cosmological constant to the 1/4. This inequality is called the Festina length. By the way, I'm not giving references a lot, and it should not be viewed that these are nameless people who did these. They're all referred to in the lecture notes. So if you want to find the references to all of these, please do consult the lecture notes that I suggested for reading material for these 3 lectures. Any questions before I go on to the next topic? Yes.
Is it guaranteed that lambda to the power 1/4 root q is always less than q?
Yes, it is not obvious. A very good question, excellent question. In other words, from this, ignoring the m, you'll get some inequality. And this turns out to be related to one version of the weak gravity conjecture too, even though I haven't discussed. So that's making a prediction, exactly.
I see. Thanks.
So that's a good observation.
There is a question from Zoom, and the question is: so no massless charged particles in ds?
Yes, correct.
Thank you.
Surprising, but yes. So that gives you inequalities, which are, of course, true in our universe. So I will talk about applications to our universe in my last lecture. So let me not talk about it now. Any other questions? Okay, so now I move on to the second topic we wanted to talk about.
Sorry,
which
there is
the
another question in Zoom.
Yes.
So the question is that are we still near or at the near extremal limit of MQ?
Extremal case, there are two extremal cases. One is this is one line, and we started with the extremal case here to use this argument. So yes, that's correct. To give this argument, you started with the extremal case to make this argument, if that was the question.
Also, there is another question. How can one derive the Nariai bound?
You mean, how did you derive this region? This is what Narai did.
Yes,
But
I think so.
maybe your question is, how do you derive this inequality? If you're asking about the second one, I refer you to the paper on the festina lente that's in the lecture notes. I won't unfortunately have time to derive it in front of you, but it's not too complicated. It has to do with the fact that the electrical field will cause the creation of charged particles, and you take into account that you're in the de Sitter space. Taking these into account gives you inequalities. It's not too difficult.
The upper bound of the black hole, I mean.
Sorry, the what?
The upper bound. The upper bound. In the figure.
The upper bound.
The
Here?
upper bound of in the figure.
In the figure?
Upper naked singular.
You mean this one?
Yeah.
Yeah. So this is part of the analysis for Neraya black hole. So if you try to solve that's a classical GR. If you try to solve for the black holes in the de Sitter space, you get only finite region of mass for a given charge. There's a lower bound and an upper bound for the mass.
Okay, thank you.
Yeah. So now the next topic I want to talk about is the distance conjecture, distance or duality conjecture. So in the various cases where we have coupling constants in string theory, they should be viewed as expectation value of fields. You never have coupling constants which are just abstractly just constant. They're always webs of some fields. That's one of the things that we know is true in all string theory. And in the context of supersymmetric theories, we typically have certain number of such scalar fields for which the web, there is no potential, so therefore they can take any web. So there's a flat direction for these fields, and you can take any web. So let me consider these cases, some of these cases where you have web for these guys and no potential. So the leading term for the Lagrangian for these theories would be, you have a bunch of scalars, d phi I, d phi j, with some coupling between them, d mu. So this gij phi should not be confused with the space-time metric. It's a metric in the phi space. And this defines a metric in the space of phi's The space of phi sometimes is called the moduli space because the expectation value of the scalar fields parameterizes all the allowed possible backgrounds that you can pick because there's no potential to zero, so you're at liberty to choose any wave you want. The moduli space of fields is typically rather complicated and it's multidimensional depending on how many fields you have. And as I just described for you, there is a metric on this space given by Gij phi, which you can read off from the kinetic term of the scalar fields. So what one sees in string theory, in all the examples of string theory, is that when you go to large distances, as I'm showing here, so these are large distance directions, these are large distances. As you go far away from the center, try to go to infinitely far away distances, it turns out that the effective field theory breaks down. That is, the description that you start breaks down. And what happens is that you get the tower of light states. So you get some light states here, which you can think about them as some tower of some states which are coming light in mass. As you go in large phi, you get the lighter and lighter here, same here, same here, same here, same here. What tower you end up getting is different depending on which direction you're going in infinity. Sometimes it could be a tower of Kaluza-Klein states where you have some part of the space decompactifying in string theory. Another tower could be a tower of light fundamental strings. So you have different situations. But if you consider this direction as parameterized by distance delta phi, as you move around in position in phi space, it turns out that the mass of the tower scales like e to the minus alpha times delta phi as delta phi grows. So in other words, the tower has exponentially light mass for large distances in moduli space. Now, this is a feature of the string theory, and we have seen it in all the examples. And so we will make but we actually have a more refined version. You could ask, what are these light towers? And in always, what we find that these light towers can only be KK tower, tower of Kaluza-Klein states, or fundamental strings, light fundamental strings. For example, if you take the dilaton in string theory and take G string to 0, you get the fundamental string become massless or light. When I say it becomes light, you might think that, wait a second, fundamental string is very heavy and so on. But what I mean by light is compared to Planck mass. So when you take G string to 0, the ratio between the string scale and Planck scale goes to 0. So the limit of G string goes to 0 corresponds to fundamental string becoming extremely light in Planck units. And if you take a compactify, let's say M theory or string theory on some manifold, and if you take the manifold to be large, again, you get a tower of KK modes, the long wavelength modes in the internal dimension, the gravitons with the long wavelengths, they correspond to very light states, and they give you a tower of states. So in both cases, note that you have at least a spin 2 in this tower. In the KK case, you can have a graviton excitation, which are these long wavelengths. In the case of fundamental string, you have all the higher spins of string excitations, including spin 2 and others, and even higher spins that becoming light. So the weak gravity conjecture says that whenever, sorry, not the distance conjecture, I mean, says whenever you go in large distance in field space, you always will have such a tower, which is either KK tower or fundamental string tower with alpha of order 1. Now here I'm writing everything in Planck units. So for example, in 4 dimension, phi has a unit of mass. So if I want to write it in a way that you can see the dimensions more properly, perhaps I should have written delta phi over n Planck. So this is dimensionless and alpha is order 1. But whenever I say, don't write it, just remind you that I'm assuming n Planck is 1. So let me give you an example from M theory. Take M theory on the circle. Then the radius of that circle viewed from the, so if you go down on the circle, you go from 11 down to 10 dimension. From the 10-dimensional viewpoint, the radius of the circle should be viewed as some field, and it's naturally parameterized as e to the phi if you want to have a regular kinetic term for it. So as phi goes to infinity, the radius goes to infinity. And so you should get the tower of light states. And in this case, the tower of light states is indeed the KK modes, whose mass goes like n over r. And this goes like n e to the minus phi. On the other hand, so in this case, you have a phi, which as you go to infinity, you get the KK mode. But if you go down to minus infinity, that's another infinite direction. In that case, r goes to 0. So if you go in this direction, as you're going towards infinity minus infinity, when you get r goes to 0, you get the membranes which are wrapped around the circle. And they give you light strings because the tension of the string you get has a factor of the radius of the string mixed with it. And this is the usual fundamental string of type 2a, as we all know. And therefore, we again get a tower of light states, again goes exponentially down, as one can check, with a distance in phi. So you get two different kinds of things. Now, in both cases, the dual objects that you get give you a new description of the theory. So distance conjecture is sometimes also called the duality conjecture, because the point of it is that when you go far away in distance, you get light states, but these light states have a meaning. They give you a dual description of the theory. They give you light degrees of freedom, which was missing from your effective field theory. It invalidates the field theory you started with. You have to rewrite your theory in terms of these light degrees of freedom, and you cannot incorporate them one by one into your theory because there are infinitely many of them. There's a tower. So the whole description breaks down, and you need to have a new formulation. And that is the duality conjecture. That means that this is the bread and butter of the duality phenomenon. Are there any questions? No questions. So dualities are quite crucial for string theory, as we know, but it's hard to derive them. So unlike the weak gravity conjecture, where we had relatively good arguments from the black hole side, the distance conjecture, we don't have a clear argument from quantum gravity itself to motivate it. So it's still missing a simple description of why it had to be the case. There are some arguments that I won't have time to discuss in these lectures, that's in the notes, which tells you that you have to get some light states when you go far distance, having to do with the finiteness of the black hole entropy. But I won't be able to cover it in these lectures, but you can look at the lecture notes. So there are some arguments, but it has not led to the precise derivation of why you should have exponential light tower. But nevertheless, it's natural to believe this conjecture because of the validity of it in all the string example we know. In fact, we can do better. Namely, we can actually predict what the exponent is. I said that mass goes like e to the minus alpha phi, but I didn't tell you what alpha is. I now claim that we know alpha, at least we have bounds for it. I claim that alpha is bigger than or equal to 1 over square root of d minus 2 when you have a d-dimensional space-time. So this is a sharp statement, and so let me explain where this comes from. This comes basically from the statement we made that the tower that you get is either a KK tower or a string tower. Because we can have only these two towers, you can actually get these bounds. So let me first do the KK tower. If you have KK tower, suppose you start with the theory in D dimension and you go down to D dimension. And then you take this intermediate space to be big. Then you can relate the tower of KK modes and find what is the relation of that with the radius of this intermediate space. And you can therefore compute the exponent. You find the exponent in that case is given by square root of D minus 2 divided by D minus D times D minus 2.
Sorry, there
This
is a
I leave as
question.
an exercise for you.
There is
Yes?
a question.
Yes?
How do you normalize phi here?
Good question. In this form, we write the phi to be 1/2 d phi d phi.
Okay, thank you.
And then this defines a GIJ metric. The metric is how you define it.
Oh, I see. Thank you.
So the claim is that if you do this Caruso-Klein compactification from a higher dimension d to a lower dimension small d, the exponent having to do with the mass of this KK tower goes like square root of capital D minus 2 over D minus D over D minus 2. This I leave as an exercise. Show this. This is not hard. Notice that this alpha is always bigger than a 1 over root D minus 2. The reason is that there's a 1 over root D minus 2 there, but there's an extra factor of D minus 2 over D minus D, and this factor is always bigger than or equal to 1. And as capital D goes to infinity, which we are not going to be, of course, realized in string theory, but if you think about it, conceptually, that will give you 1. So the larger and larger D will give you the bound you want in terms of the being bigger. Any questions? So I have shown that alpha is bigger than or equal to the square root of D minus 2, at least for KK tower. For the string tower, which actually much easier, you can actually use the string theory itself because fundamental strings is what is the conjecture that's arising. It turns out the coupling of the dilaton is universal in string theory. And using the universality of the coupling of the dilaton and the string tension, the relation between these, you can find what is alpha for the string tower. And it turns out it saturates this bound. So for string case, the alpha that you get is exactly 1 over root D minus 2. So that basically the distance conjecture is that you always get a light tower in an exponential form where the decay rate is always bigger than 1 over root D minus 2. And this is saturated only if it is a string one. Yes, you have a question.
Yeah. So these formulas are strictly for small d greater than 2?
This is only for D bigger than 2.
I see.
Notice that for D equals to 2, we cannot freeze the internal geometry.
Sorry, can you say it again?
Because of the fact that scalar fields fluctuates. So I'm never compactifying to 2-dimensional. I'm always above 2.
I see. Okay, thanks.
If we want to freeze the geometry. Any other questions? Okay, so notice that the distance conjecture, duality, distance or duality conjecture, whichever you want to call it, it implies that any consistent quantum gravity needs extended objects. In other words, the point particles will not be enough. Even if you didn't assume string theory, you'll automatically be driven by this conjecture to demand that there must be some extended object. And why is that? Well, if you take the theory that you're given and put it on a circle of radius r, as I told you, r goes like e to the phi, and as phi goes to minus infinity, you find that if you just had point particle theory, all the states become extremely massive because you have a KK modes which are becoming very, very heavy in the limit of small radius, and just get the dimensional reduction of the theory to one lower dimension without any extra light states. But the theory says that there must be extra light states as phi goes to minus infinity. And the only way that can be is that when you take the radius to be small, there should be some object which feels the size, which is global, feels the size of the circle, which means it should be an extended object. A point particle theory cannot do this. So therefore, the only way that you can have a distance conjecture satisfied in a quantum gravity theory is to have extended object like strings or membranes. So this is quite interesting that we can reverse it and give a logic for string theory if we have a better understanding of why distance conjecture had to be true.
Can I ask a question?
Yes?
So here, are you assuming that all the quantum gravity has an non-trivial moduli space?
No, I'm not assuming that. For example, M theory does not have moduli space.
For M-short case, you're creating a moduli by compactification, right? So and applying.
I'm
this
just saying if you have moduli space, like in compactification, or like in type 2B without compactification, you have moduli.
Okay.
The
Thank you.
coupling axial delta. Yes? Any more questions? Okay. So there is a generalization of the distance conjecture. Now, the idea is that I told you that if you look at the field space, scalar fields giving VEV, it gives you a notion of distance. But sometimes these fields should be viewed as components of the metric in the internal geometry. For example, in the case that I just told you, the g theta theta, the component of the metric in the circular direction was related to the phi. So therefore, if there is a distance conjecture, it cannot be just restricted to scalar fields. It should be more general. But we usually don't give any VEV to any field other than scalars, otherwise you break Lorentz invariance. Therefore, we cannot talk about any other field. Well, that's not entirely true. In the context of anti-de Sitter or de Sitter, we do give VEV to the metric degree of freedom, which is not just Minkowski, it's not Lorentzian. It's not just a constant flat metric, so therefore you have a metric, and so you do have a VEV for G mu nu, which is the basically ADS metric, or de Sitter metric. So then there's a notion of distance in this space, which is related to the value of the cosmological constant. It turns out that the natural notion of distance goes like log of absolute value of lambda with some coefficient. So that, how do you define that? Well, you can use the notion of the metric in the metric space with the usual, some definitions like this, for example, G mu nu, so some integration like this can define a notion of distance between varying G. Using this kind of definition, you find that there's a notion of distance which scales like log lambda. In other words, if you change lambda, this is the cosmological constant, by some value, it's as if you're moving the distance by log of it in absolute values, of course. Lambda could be positive or negative, and you have to take an absolute value of these to get the distance. So the generalized distance conjecture says that you should also view this as a distance. And what does that imply? Well, if lambda goes to 0, that corresponds to distance goes to infinity. Why? Because distance goes like log of lambda. So lambda going to 0 is another infinity. But we just said that this should give you a mass of the form e to the minus alpha times the distance. And so this will tell you that there should be something which goes like lambda to some power. So this is interesting in the sense that as lambda goes to 0, you get this thing goes to infinity in this way. And so you get some particles which are light, which scales as lambda goes to 0. Put an absolute value here, because this applies both to ADS and de Sitter. In fact, we have a lot of evidence for this. I see a question in the chat.
Yeah, the question is that the charge mass double bound we had in DS also was an upper bound on lambda right?
Well, if you
Lambda
fix the
right.
mass, you can view it as bounds, as a lower bound. In other words, we had a relation of the form m was bigger than square root of q times lambda to the 1/4. So if you say that you have a particle, that gives you an upper bound on lambda.
Okay.
Is that what you were saying?
Yeah, I think so. Yeah. Thank you.
Okay, so we have learned that m goes to lambda to some power as lambda goes to 0. This should be true. And is it true or not? Well, we have ADS examples. We can check. We know a lot about ADS examples. And so whenever we get an ADS space, some internal spaces are also part of the story. So as you take lambda to 0, it turns out that the radius of the ADS goes to infinity. That's what lambda goes to 0 means, because after all, r is related to the lambda to the -1/2. So as the radius goes to infinity, it turns out of the ADS, it turns out that the radius of the m, the diameter of the m, also goes to infinity at the same rate. In other words, you get a light tower having to do with the Kaluza-Klein modes of this internal dimension. So again, we see that the distance conjecture predicts this, but this is actually realized in examples. It tells you that you cannot have an ADS just by itself. You cannot just have an ADS with an internal manifold, which is frozen to be, let's say, Planckian. If you make ADS big, it turns out that diameter of that manifold should also grow in such a way that you get a light tower. And that's what we know is true from examples. Now, it doesn't mean that all of M should grow, but some part of M should grow. For example, in the ADS 3 times S3 times K3 examples, if ADS3 gets bigger, S3 gets bigger, but K3 doesn't need to get bigger. But the main point is that you do get a tower of light states this way. And there is no example known for which you can freeze the geometry completely. In the example I just told you, and in essentially all the examples we know of in ADS, the mass of the Kaluza-Klein states scales like lambda to the 1/2 as lambda goes to 0. So the exponent is a half there. I think I have run over my time and I'm basically finished with what I wanted to say. So we have seen that these two conjectures, the weak gravity conjecture and distance conjecture, are motivated by principles from string theory. The weak gravity is more easily connected to some ideas with black hole. The distance conjecture is not as easily connectable, and I haven't given you much connection yet, but there are some connections. But main motivation of it comes from string theory. They both have been tested quite a bit, of course, in various cases. And there is an interrelation between them, which we can, some of the aspects of it is discussed in the lecture notes. So they are kind of not completely independent. There's some relation between them. For example, when we say m is less than or equal to g, g itself can be viewed as parameterizing a moduli space. So as g goes to 0, that corresponds to infinite distance. And this gives you that tower, which is related to that mass going to 0. So again, we see the relation between the weak gravity and distance conjecture. And this happens again in various kind of contexts, that various kind of aspects of swampland reinforce each other in different ways. So I think I will stop here and let you ask questions if you have some. Thank you.
Questions?
In your M theory example, I'm wondering how the tower of M5 branes wrapping the circle compares to fundamental strings.
They are more massive. So this is indeed, people have also studied that there is not just one tower, there are other towers of states. And it turns out that always the lightest tower is either a string or KK modes. And in the case of that you just mentioned, M5 brane wrapped around the circle would have a mass which is higher parametrically than this one.
I see. Thank you.
Yeah.
So a couple of questions. So if going back to the formula that you wrote where D was strictly greater than 2, if I still nevertheless want to compactify up to 2 dimensions, should the conclusion be that I do not expect such infinite number of massless or light states?
You cannot freeze, the question doesn't exist really.
Sorry?
You see, the point is that the phi itself cannot be frozen at the one value. You have to integrate over it. This quantum fluctuation doesn't allow you to ask that question.
I see. Okay. And later I think in a couple of slides later, you wrote a formula for distance in terms of the capital lambda. So is this distance in the sense of, my question is, does it follow, does it satisfy some kind of Schwarz inequality that I would expect any distance function to have?
Well, this is a bit tricky in the sense that the metric space is not definite. So unlike the other ones, so it's a bit more heuristic, this one. So yeah, one has to take this equation as a kind of a derivation involving some choice of metric space. So there are kind of different kinds of definition you can give on the metric, but there is not a definite metric distance because Lorentzian distance.
I see.
So it's a bit different from the usual one.
Okay. Thank you.
So, but no matter what you do, you get the log feature.
Kumlun, can I ask a question about your generalized distance conjecture with the
Yes.
cosmological constant lambda? So it seems
Yes.
that if you consider background with strictly lambda equal to 0,
Yes.
for instance, if we seek for a, let's say, Calabi-Yau compactification to Minkowski space, would effective field theory description be always pathological? That's what you imply?
No. So let me explain. In that case, it implies that there is no marginalized space for which lambda is anything but 0. That means that you should not view this as part of a marginalized space in other words, there is no theory for which you can approach 0. Calabi-Yau is lambda is strictly 0. You see what I'm saying? In other words, positive lambda and 0 are infinitely far away. And you cannot connect them. If Calabi-Yau was part of the lambda positive case as a limiting case, then the contradiction that you're saying would arise.
Are you saying that a strict Minkowski space, lambda is not,
No.
Okay,
Exactly.
I see.
Just a good example of it is, let me say it in a better way. Instead of dissiter, you could have asked me for ADS.
Yeah.
Right? You could have said the Minkowski, am I predicting that there's infinitely many modes in the Minkowski space? I say no.
Yeah. Right,
And then you
right.
say, well, but there is Minkowski space. So let's see what happens in that case. You have like ADS 5 times S5. If there was no S5, you would say that ADS 5 become infinite, you get infinitely light towers, which means that but indeed you're forgetting about the S5 piece. S5 piece is also getting large, so you get a 10-dimensional Minkowski space. So when you view it from the 5D perspective, the extra 5 looks like infinite tower. Do you see what I'm saying?
Yeah.
So there's no contradiction with a single Minkowski space with no light states.
Yeah.
But now the Minkowski space is 10-dimensional, not 5.
Yeah. Thank you. Yeah.
So there's a question from Zoom, and the question is that, can I consider the energy scales of the effective field theory as a moduli field in the generalized distance conjecture? If so, how do I understand the gapped low energy effective field theories or low energy effective field theories without tower of light state?
So can I consider the energy scales? What does that mean exactly? Energy scales are not fields. So what do you mean by fields? You can consider energy scales, but they are not fields. Now, you can trade the distance. You can do the following. So there's one version you can try to say, I'm not sure if this is what you're trying to say or not. So if you take a marginalized space of these scalar fields, you can start with an energy scale. Let me call it lambda, which is the cutoff of your effective field theory. Now, as you go far away in distance, there will be some state whose mass become lower than lambda, and that you had ignored before. So that means that as you're going towards infinity, you will get regions for which these new states appear, and so therefore you will have to delete far distances in a moduli space if you are trying to keep your effective field theory valid. So that if you have an effective field theory with a given cutoff, you will have a finite moduli space. The infinities will be chopped off. That's what will happen.
Any other question?
I have a question. So, is it possible to consider the distance conjecture on conformal manifold? I mean,
On conformal manifold, what do you mean by conformal manifold?
theory of, I mean, this in special case of CFT.
So the distance conjecture can be applied, and it has been applied to the case of ADS, in the case of holography, for example. So you can take ADS times some space, and then there are some fields in this ADS theory other than lambda. For example, you can take ADS 5 times S5, and then there's a tau, right? You could ask what happens if tau goes to 0 or this and that. So there's that notion of distance, and the distance conjecture applies also to that.
I see. Thank you.
Yeah, and this has actually been discussed in papers. It actually turns out to be related to the appearance of higher spin symmetries in conformal theories. So precisely the infinite distance limit in these moduli spaces are precisely the points where you get the approximate higher spin symmetry.
Can I ask a naive question? So, at the beginning of the talk, you said that we can use the distance conjecture as a criteria for a swampland. But so now that you introduce a generalized version of it, so which one should we use? Or
Well, they are related. They are not contradictory. The statement is that any field in your theory gives you a notion of distance, and you should use the proper notion of distance for any field, and for that it will apply, whether you use it for scalar or metric or any other degree of freedom.
okay, so the normal version of it and the generalized version is not like which one. So none of them is stronger than the other, right? It's just
No. Generalized version is stronger. The original version is a subset. It applies only to scalar fields.
Okay, thank you.
Yeah.
Any other question? Okay, if there is no more question, then let's thank speaker again. Thank you very much.
Thank you very much. See you tomorrow.
You said that for the distance conjecture, we'll always have at large distance, either KK tower or fundamental strings. Is there any other possibility that we have a light or tensionless extended object?
Well, we don't have any examples of it, so we believe no. That's what's called a string emergence. The only thing that can emerge is string other than KK. It's surprising, but that's the case.
Okay.
So I have a question.
That actually gives you a motivation of why we should still call this theory string theory.
So, I have
Because that's the only thing that can be light.
If you can view the black hole as a particle, then can you say something from the weak gravity conjecture that, if you say something from the weak gravity conjecture? So.
Sorry, if I can get what? I
Yeah.
didn't catch you.
So, from the weak gravity conjecture, there is a condition for a particle of mass and charge, and if you can think the black hole as a particle, then so let me ask this question. So how can you distinguish the black hole and particle?
How can I distinguish the black ring from a particle?
Yeah. How can you distinguish the black hole and the particle?
Well, the black ring is charged under a gauge field.
Sorry?
The black ring is charged under a higher form gauge field.
I see. So different charges. I see. So that is the how distinguish. I see. Thank you.
Yes. Yeah.
So I have another question about yesterday's argument about
Yes.
the completeness. So completeness conjecture also holds for the non-invertible ones, right?
Completeness conjecture is actually follows from non-invertible symmetries.
And so non-existence of the non-invertible or topological object can be argued in terms of the black holes too.
The argument for them is a bit indirect. So no, I would say that the completeness comes from the fact that you cannot have a non-invertible global symmetry is the more general argument. That there's no topological operator.
I see.
So the black hole is a weaker one.
Okay.
I suspect that one can try to make the black hole argument stronger to make it work, but nobody has done it.
Okay, thank you.
Thanks.
Okay, thank you very much. Yeah, see you tomorrow.
Bye-bye.
Bye.
Bye.
Okay, good morning, everyone. Welcome back. It's time for us to resume, and Professor Benini will continue his lectures on entropy of ADS black holes. So please.
Thank you. Can you hear me? Yes? Okay. Okay, so yesterday we discussed at length some properties of BPS black holes in ADS5. In particular, we discussed their entropy, and their grand canonical partition function as computed from gravity. And as I stressed, focusing on a specific example, but the ideas are general and applies to black holes in other dimensions of other types. And today, our goal would be to try to reproduce this feature, the classical feature that we described, from field theory. And then from there, we try to go beyond those classical features. So our goal would be to count the states from the quantum field theory, the dual quantum field theory that lives at the boundary of ADS. And in particular, we would like to count the number of BPS states. So of course, when we look at BPS states, with the given charges, so we fix the charges of the black holes, and we would like to count the BPS states with those charges. And if you are able to do that, this is essentially a non-perturbative definition of the entropy in the statistical physics sense, and we expect that the leading contribution should be the Bekenstein-Hawking entropy, but then we can try to, well, we can look for all types of corrections. Now, if you apply this strategy, there is a small caveat that we should take into account, and to which we will come back towards the end of these lectures, which is the following, that if we count the states from the point of view of the boundary theory, so here we have our ADS, here is the black hole. What we are doing is to count all possible states, all BPS states, with the given charges, not necessarily just the black hole states. And for sure, there are some states that do not pertain to the black hole. For instance, we can have states of gravitons that hover around the black hole, and these gravitons will have some BPS states. Those probably we don't want to call them black hole states, but they will be counted by the boundary theory. Now, we could try to propose a definition for what a black hole state should be. And for instance, one possible definition would be that we look at the near horizon geometry of these black holes, and we identify states that are described by the field theory, which is dual to the boundary ADS2 that we see in the near horizon region. This is some possible definition that might work. However, that might work in the bulk. However, it is not clear how to extend this definition to the boundary theory. So, because in some sense, this definition uses bulk locality, which is not obvious how to see from the point of view of the boundary theory. However, if we are looking at large black holes, so black holes whose charges Q and J are of order n squared, then the entropy of these black holes will be very large, and in particular, most of the states will be black hole states. And so in this sense, we expect that at least in leading order, most of the states will be black hole states, and we can... or is it? Maybe if I write larger, could be better. Let's see. Wow, this is not good at all. Is this better? Is it better? Yeah, I will move that in the back as well when I go there, yes. I will also try to write larger. But maybe from the next time, because now I'm sure it will take me 10 or 15 minutes to understand how to do that. Okay, good. But if it's not yet clear enough, just tell me that I will write larger. Yes, thank you. Anyway, so the idea is that if we consider a large black hole, then most of the states will be black hole states. And so at leading order, this counting from field theory should reproduce the entropy of the black holes, but we have to keep in mind that we're going to count all states in the bulk, not just black hole states. Okay, with that in mind, so how do we count states? Well, a convenient way is to use, in fact, a grand canonical partition function. So this object schematically is a function of a variable, which is our fugacity. This is a sum over all states in the theory of this fugacity to the charge of the state. And we can write this as a sum over all charges of a number, which is the degeneracy of states with the given charges of y to the q. So now, if we are able to compute this object, there are two strategies or two types of computation we can do, which are similar but slightly different. So one is a sort of Lorentzian computation. So essentially, we can try to extract this degenerate of states. This will be the microcanonical entropy. So in order to extract this, we can just do a Fourier transform. And we can rewrite this. We can define y, the fugacity in terms of a chemical potential. And so we can rewrite this as an integral for delta that goes from 0 to 1. So here there is a log. So now we can assume, if we assume that there are large degeneracy of states, so that this object is large, and the charges we are considering are large, we can compute this integral in the saddle point approximation. And then if we do that, we reproduce the standard results in statistical physics that, because when we compute this in the saddle point approximation, we are taking a variation of this to set to 0, but this precisely the Legendre transform of this object. And so we obtain the standard result that the entropy S of Q, the microcanonical entropy, which is the logarithm of this degeneracy of states, is just the Legendre transform of the logarithm of the index. So this, we evaluate this at the extremal value for delta. So this is one computation we can do. And we can use this computation to try to match the entropy computed from field theory with the Bekenstein-Hawking entropy computed from gravity. Let's see if this is good. All right. There is a slightly different Euclidean approach that we can take, which is the following. So the grand canonical partition function can also be computed or represented by a path integral of the theory on S3 times S1. So we take the theory, we go to Euclidean signature, and then we compactify time. And so we can represent the index as the path integral of the partition function over well, some spatial manifold, and in this case will be S3 times S1. So this is going to compute the same object with a suitable regularization. And then we can apply the rules of ADS-CFT, and by holography, a partition function of the boundary theory would be equal to an Euclidean gravitational path integral, or string theory path integral, and I put this object in quotation mark because we don't really have a good definition of this object, with fixed boundary conditions. So essentially, we fix the boundary conditions to be S3 times S1. So the metric will be the metric of the theory here. There could be some other background fluxes. And then we are supposed to do a path integral over all possible gravitational field configurations in the bulk that have the correct boundary conditions. So here we should sum over all configurations. So the problem with this is that we don't, as I say, we don't really have a good definition of this object. However, we can take the point of view that the boundary field theory defines for us what this object is. And then, since we are working in this semi-classical regime in which gravity is weakly coupled and it's close to Einstein gravity, then we can try from the answer to, first of all, compare with a semi-classical expansion of gravity and possibly try to understand what rules we should apply to this semi-classical expansion of gravity, which is not obvious, right? So this is a general strategy that we can try to do. Unfortunately, there is a problem, and the problem is that the theory is strongly coupled. This is part of our regime in which we are working, and so computing the thermal partition function for a strongly coupled theory is extremely difficult. So to begin with, and this will be the main non-perturbative tool that we will use, we can employ a supersymmetric partition function that will be protected by supersymmetry and that we will be able to compute exactly. So we use a supersymmetric partition function. So this is called index. And essentially what we do is to, we still have a sum of our states, but if we insert a -1 to the f, so in other words, we have periodic boundary conditions for fermions, and then this object will be protected by supersymmetry, and it will be computable exactly. And towards the end of this lecture, we'll come back to this point, to the relation between the thermal partition function and the supersymmetric partition function. However, as I said, so essentially the point is that this object is exactly computable. And in fact, this is an object that does not depend on the continuous deformations of the theory. So if the theory has a continuous deformation to weak coupling, we can use this continuous deformation and we can compute this object at weak coupling or in the free theory. Alternatively, for theories that do not have this continuous deformation, we can still use supersymmetric localization techniques that allows you to evaluate this path integral exactly. Now, of course, since so this is a supersymmetrically protected object, this object will count BPS states and only BPS states. And so for this reason, we can use this object only for supersymmetric black holes. Okay. So now, if we try to use this object to count the states in the field theory, of course, there is an obvious complaint that one might have that this object contains -1 to the f, -1 to the fermion number. And so it's not really computing the number of states, but it's computing a weighted number of states in which bosonic, which is bosonic minus fermionic states. And so there might be large cancellations, and this object might underdetermine or undercount the number of states, and so it might miss to compute the entropy of the black holes. However, I would like to give you an argument, while instead, we can argue that this object should contain the entropy of the black holes. And the argument goes as follows. Essentially, it's based on the fact that we can think of the black hole solution as an holographic RG flow. So if we take our solution, so here is some radial coordinate. So at the boundary, we have asymptotically ADS. Then in the middle, there will be the black hole solution with some horizon. And in the near horizon region, we have some ADS2 times S3 in this particular case, where really ADS2 is fiber over S3. But so what we can do, so we can take this black hole solution in which the fields will have various profiles, and we can use the rules of ADS-CFT to read off what these fields represents from the point of view of the boundary theory. In particular, the fall-off of these fields will correspond to the fact that the boundary theory is placed on a particular background. For instance, the boundary theory is placed on S3. But then the fact that the black hole has charges also implies that there is some non-trivial background on this manifold. So we can regard this transformation or this deformation as some relevant deformation that triggers an RG flow. And so the four-dimensional theory starts flowing. And this flow will represent a flow across dimensions because in the near horizon region we have ADS2. So this ADS2 should be dual to a one-dimensional CFT times some compact manifold. So we can think of these solutions as an holographic RG flow across dimension in which we start with the four-dimensional theory, we do some relevant deformation, and we end up with a one-dimensional conformal quantum mechanics. Now, as was stressed yesterday, so we end up with a one-dimensional CFT, and if conformal symmetry is not broken, then this means that the theory is a topological field theory, because, as was discussed, for instance, the fact that the stress tensor is traceless means that the Hamiltonian is zero. So this theory really just counts a number of states with zero Hamiltonian. And in fact, these states will correspond to the BPS states of the black hole. Now, these black holes preserve one complex supercharge that I will call Q. And therefore, what we have is a one-dimensional n equal 2 quantum mechanics. And we can see the index as the Witten index of these quantum mechanics. So what can we say about this Witten index? Well, the near horizon region, because of ADS2 and because of the presence of this complex supercharge, has some superconformal symmetry. This superconformal symmetry has SU1, 1/1. So let me write it here. So we have SU1, 1/1 superconformal symmetry in the near horizon region. The bosonic part of this symmetry is in fact SL2R times U1R. So SL2R is the isometry of ADS2, and U1R is a superconformal R symmetry. Now, this ADS2 that you have in the infrared is dual to the normalizable ground states of these quantum mechanics. And what can we say about this? Well, if the conformal symmetry is not broken, and I will come back to this point in a second, then the states will be invariant under SL2R. They will also be invariant under the fermionic generators that are in this group, because these fermionic generators correspond to the Killing spinors of the ADS2, and there are Killing spinors that are preserved. 2 of them correspond to the supercharge, and 2 of them arise in the near horizon region. These are the conformal generators. And so we can use the algebra of this superconformal algebra. In particular, schematically, one of them looks like the following. So they say, so the states are annihilated by L0, are annihilated by the conformal generator, by the fermionic generators, and so they must be annihilated also by the R symmetry. So we can conclude that the states have vanishing superconformal R charge. Okay, so what? So suppose that we can, typically this is what happens, suppose that we can find some R charge. So let me stress, this is the superconformal R charge. So suppose that we can find some R charge, not necessarily the superconformal one. Let me call it R0, such that -1 to the F can be written as -1 to the R0. Then we can write the index in the following form. So this is a trace of -1 to the F, y to the Q. So we can write it as E to the I pi R0 plus 2 delta Q. Okay, when again I'm writing y as E to the 2 pi I delta. And so we can identify the exponent here as some trial R charge that I will call R of delta. In other words, we can think of the index as an object that, as we change this delta, explores a space of possible indices in which, instead of using -1 to the F, we use -1 to some R charge. Now, if we are in some favorable situation in which the space of R charges is connected, and so as we explore the space of possible R charges, we explore all of them, and moreover, assuming that there are no accidental symmetries, so that the superconformal R symmetry is visible in the UV and does not arise accidentally in the infrared, then there will be some value of delta such that this object here is the superconformal R symmetry. But then this means that the index for this particular value of delta will become the trace of -1 to the R superconformal, but we just argue that for the black hole states, this superconformal R symmetry should be 0. And so effectively this becomes the trace of 1, and so in fact we are counting the states without any sign. So this shows that under these assumptions, it should be possible for special values of the fugacities, essentially to cancel the signs, and the index should exactly capture the degeneracy of black hole states. Yes, yes. So this is 0, as we argued, on black hole states. Yeah, so this is what we showed here. So this R is the R superconformal. So essentially we said if it is true that the if you want, that the conformal symmetry is unbroken on the states, and the fermionic generators are unbroken on the states, then from the superconformal algebra, it follows that the superconformal R symmetry should be 0. So this R is the superconformal one. So this was our result. So L0 is 0, right? Because so the states are invariant under the full SL2R, in particular under L0. These are the fermionic generators, so essentially this is the only generators that we are left with, and we conclude that the charge should be 0. Yes, the point is that it's not immediately obvious that the black hole solution preserves the superconformal R symmetry. What is obvious, at least classically, is that it preserves the conformal symmetry because this is a isometry of ADS2, and you can check that there are Killing spinors, so you see the fermionic generators. Perhaps this is not immediately obvious, but it follows from the algebra. Now, of course, here there is an assumption, and the assumption is that the conformal symmetry is not broken in the infrared. So now we should compare to the analysis that we heard yesterday about the near horizon behavior of the black holes, and we heard that in general the conformal symmetry is actually broken. However, the discussion was without supersymmetry, and in fact, unfortunately, there was not enough time to discuss the case with n equal 2 supersymmetry, but what they found is that with n equal 2 supersymmetry, the ground states, the BPS states, in fact, are not lifted, and so they remain as a delta function. If you remember yesterday, the possible density of states compatible with conformal symmetry, there was a delta function, and it turns out that with n equal to supersymmetry, in fact, that delta function is there, and so the states do not break conformal symmetry, and in fact, they are the states of this topological field theory. Now, of course, here, so, okay, we conclude that this result should be true. Of course, we need to find what this delta is, but this delta is relatively simple to find because if we take a derivative of this index with respect to delta, we bring down a q. So essentially, this derivative computes the expectation value of q, which is the charge of the black hole. So we can write, yes.
Could you explain what is the trace here? Which Hilbert space we are talking about?
Okay, so this object here is the index. And so far I'm general because this argument applies to many different indices and will be specific to any four superior males in 4 dimensions in a moment. But this is the general form of an index. So there is a -1 to the fermion number. There is typically some Hamiltonian that we need for regularization. There is e to the minus beta h, but this h is a supersymmetric Hamiltonian, which is invariant under some supercharge. And so in particular, this means that actually the states captured by this index are the ones for which this h is 0 and there is no dependence on beta. So for that reason, I remove this, and maybe here we can put BPS. So we'll have trace over BPS states. And then there are some fugacities. So these are some variables.
No, I guess my question is, you were considering just one fixed black hole solution, I thought.
Let's see, no. So this is the index of the boundary theory.
Oh.
And so this index captures all possible states in the bulk.
Right.
And since it is the grand canonical partition function, it contains all possible charges.
So
this should contain information about all possible.
So it doesn't mean that the so that's my confusion is so you do not consider just one fixed solution in ADS asymptotical ADS5?
Yes. So in the bulk, we'll have a fixed black hole.
Yeah.
Because we fix the charges of this black hole.
Right.
And we'd like to count the states of this black hole. Now, it is convenient, but it's just a tool. Instead of working at fixed charges in the microcanonical ensemble, it's convenient to work in the grand canonical ensemble. So we consider all possible states with all possible charges, but we have fugacities that keep track of the charges.
I
And so
see.
eventually, we have to do a Legendre transform and go from the grand canonical to the microcanonical and extract the degeneracy of states for fixed charges.
I see. Thank you very much.
Yes,
I see.
thanks.
So you consider all charges. I see.
Yes, yes. And then, yes, and then essentially, as I said, we can either transform and go to the microcanonical ensemble, or we can try to match directly this object with gravity with a gravitational path integral. But here I have in mind that I would like to go to the microcanonical ensemble.
So does your argument hold for any kind of ADS5, or you have an equal Cauchy-Fourier and its holographic dual in mind?
So, as I say, so here I'm very general, and this is valid in general for theories in which the black holes have one complex supercharge. It can be in very different dimensions. It could be in ADS4, ADS5, ADS6, and so on.
Okay.
So then, in the next, I will specialize to the case of n equal 4 Spirian Mills, but what I'm saying is valid for all these black holes.
But here you replace the fermion number by R charge. Is R charge, so is it guaranteed that R charge of the state is always integer?
So, I mean, so let's see. So, of course, you need, I mean, we are working in a supergravity, which is due to a supersymmetric theory in which we do have an R symmetry. And in fact, the example, since we need at least one complex supercharge, in all those examples, there is an R symmetry.
Yeah.
So for instance, if we were working with n equal 1, then all these arguments will not be valid.
Yeah.
And in that case, okay, we could live in a supergravity theory without an R symmetry. But since we need this amount of supersymmetry, there will always be an R symmetry.
Yeah, I know, but the R charge of the states should be integer, otherwise the replacement of the fermion number by R charge doesn't make sense, right?
Yeah, no, that's true, that's true. So what I said is that, so let me see here. So first of all, we look for some R charge, which is not the superconformal one, such that minus 1 to the F is minus 1 to this R charge. And this is typically possible. I'm not sure if every possible theory this is true, but in most theory, this is what happens.
Here the R charge is for the R charge in the quantum mechanics or for the...
No. So this will be, so let's see. Well, I mean, assuming that the non-accidental symmetry is the same, but here what I have in mind is a R charge of the UV theory.
UV, for this theory, or whatever.
For the theory in this example, yes, yes. But again, this is not a superconformal R symmetry. This is just one supersymmetry. And typically this is possible. I'm not claiming that it's always possible. So I'm working on the assumption perhaps that this is possible. But then we can combine this I don't know, reference R symmetry with flavor symmetries to generate a space of possible R symmetries. And again, under favorable assumption, in that space, there will be the superconformal one. So there are a few assumptions that one need to make. No. So one can study, for instance, the n equal 2 super Schwarzian, and one can see whether supersymmetry is broken or not, whether there are vacua that preserve supersymmetry, and there are. So this is different from without supersymmetry or n equal 1 supersymmetry. So with n equal 1, for instance, supersymmetry is broken. There are no states, or at least the density of states goes to 0. With n equal 2, yes, there are the states, and in a sense, they have to be there because they are protected by the index. So for sure, we know that the index, the fact that the index is non-zero tells us that there are some BPS states, such as bosonic minus fermionic, is equal to the index. So as long as the index is not 0, that number cannot be 0. And what we are saying here is that we can make a choice of the R symmetry such that the index is actually counting all of them with sign +1. Yes.
Quick question.
Yes.
In the right blackboard, if you find the delta to find the right superconformal L symmetry, was it checked that it matches with what you would find if you do an analysis of the killing spinors in the ADS2 region? Like I saw something like that in paper, I think, by you in the ADS4 black hole, but I was wondering if one can check it for the ADS5.
So what check, sorry, you would like to
that you
do?
can determine the superconformal R symmetry by looking at the algebra of the killing
Yes.
spinors and killing vectors in ADS2 and compared to the superconformal charge R symmetry that you get from the right blackboard.
Yes, yes,
whether
yes. So this
that matches. Yeah, that's just.
Yes, yes,
if
it
you
does. So, okay, I'm not sure if all possible cases have been checked, but essentially, this is the statement that, so this procedure that you do in the field theory that you can call I extremization matches with a procedure that you do in gravity, which is the attractor mechanism. So you can see that as you flow, so you start in the UV with some superconformal algebra, and you flow in the infrared, and in the near horizon ADS2 region, there is a different superconformal algebra in which the superconformal R symmetry is a different one, but it's precisely the one that is generated by the killing spinor, and is the one that is selected by this delta that have a dual in supergravity corresponds to the attractor mechanism. So at least classically everything works.
Specific choice of y, is this only works for this beta equals 0 limit?
For what, sorry?
So this high temperature limit. Do you? So you first when you like write this e to the minus beta h and delete it, you.
I didn't take any high temperature limit. Sorry.
But you just like choose the Hilbert space to be BPS states. Then that's so index like for the regularization e to the minus beta h.
Yes.
So you just like discard that term by choosing the Hilbert like BPS substate in the
Yes.
trace. I'm asking your trick of this taking the y to be -1 to this y to cancel the -1 to the f can be performed in the presence of the regulator e to the minus beta h.
So let me specify. So I'm not chasing. I'm not choosing. I'm not doing if you want low temperature. I'm not taking beta to infinity here. So in this precise the difference between the index and the thermal partition function. So in the index, let me write it again. So an index is an object of the following form. So it's a trace over all states -1 to the f. And then typically you have e to the minus beta, and this h is a supersymmetric Hamiltonian that you write as some anti-commutator of a supercharge with itself. And then possibly you can have some other fugacities. And the point is that for all states, so this is h, for all states for which this h is not 0, the states will not be annihilated by both Q and Q dagger, so you can use either Q or Q dagger to generate another state. These other states will have the same value of y, but we have opposite -1 to the f. So
the trick doesn't work for non-BPS state.
So the point is that all states which are not BPS will not contribute to this object. Because there will be a pair of states for which this is the same, this is the same, but the sign is opposite.
Yeah, I agree. But
so this trace, which is, if you want, this exponential here is just needed to regularize the sum, otherwise it would be divergent. But in fact, only the BPS states contribute. For generic value of beta, you don't have to take a limit on beta.
Yes, but the trick that you discard the -1 to the f in this BPS some of our BPS state was quite nice. Okay, so I was wondering.
Yes. So this is I'm not using any limit on beta, and this should be valid in general under the assumption that I described.
I see. Thanks.
Thanks. Okay. So what I wanted to say is that we need to figure out what this delta is. But this delta can be computed by taking a derivative and observing the Q goes down. And if there are no signs, then this becomes the expectation value of Q. So we get an equation where this is the expectation value of the charge operator. So this is the charge of the black hole. So this is the equation that determines the value of delta, this delta bar, such that if we want R of delta bar is a superconformal charge. But in fact, you recognize that this is nothing else than precisely the equation that you impose when you compute the Legendre transform. So in fact, this value of delta is not some new value. It's precisely the value of the chemical potential, which is selected by the Legendre transform. And this is nice, because we know that we have to do a Legendre transform to go from the grand canonical to the microcanonical. So it would be surprising if there is another value of delta that you have to use instead of the one selected by the Legendre transform. So as I said, this sort of argument or procedure goes under the name of A extremization. And you can think of it as a sort of generalization to 1D of the A maximization that exists in four-dimensional N equal 1 theories to determine what is a superconformal R symmetry, and there are similar extremization procedures in 3 and 2, and then this is in one dimension. Now, however, let me stress this argument is only valid, we expect it to be valid only at leading order, because what we used was the property of this near horizon region of ADS2. These properties are surely not true if you are away from the near horizon. So in particular, for a gas of gravitons that hover around the black hole, should not be true that all the states have the same statistics and there are no cancellation. And in fact, we can explicitly check, for instance, for a gas of gravitons in ADS5, that there are cancellations. So the index is not the same as the thermal partition function. However, once again, since we will look at large black holes, most of the states will be black hole states, and so for most of the states, there will not be cancellations. But among other states, there will be cancellations.
Can I ask a question?
Yes.
So maybe I'm lost. So we are considering four-dimensional CFT.
So, sorry, where are you?
Here.
Oh, okay.
Yeah. So you want to count the state in four-dimensional CFT, right?
Yes.
But why we are considering here the one-dimensional CFT here?
Yes,
so
because of this interpretation of the black hole as an RG flow. So you start with the four-dimensional theory, but you can think of the black hole as holographically as the fact that you take the four-dimensional theory, you put it on S3 with some background, and then the theory flows, because this is a relevant deformation, there is a scale, and it flows to one-dimensional theory. Essentially, this is the quantum mechanics of the modes on the sphere, and the index of the four-dimensional theory is the Witten index of this quantum mechanics of all the modes. And if you want, you can, in the very far infrared, we can say, okay, only keep the infrared CFT that in one dimensions will be a topological field theory. And
So
the point is that this is not empty because of N equal to supersymmetry.
Then the bulk side black hole can be captured by the IR degree of freedom in CFT side, right?
The problem is that we don't really know what is the description of the infrared degrees of freedom. So we do something very similar in higher dimensions. You can start, I don't know, with the 6-dimensional 2,0 theory. These are very typical things that people do. You put this 6-dimensional theory on a Riemann surface, for instance, and then you claim at low energy, I will go to some 4-dimensional theory, maybe some interesting non-Lagrangian theory. You can study it, so on and so forth. And you can, if you want at low energy, you can just use the infrared CFT. In some cases, you can identify a Lagrangian for it. It could be, for instance, N equal 4 superior Mills. In some cases, it's a non-Lagrangian theory, which is interesting to study. So here, the philosophy is similar. The only caveat to be careful about is that without this supersymmetry, you would not really have an infrared CFT. Because as it was discussed, even though there is an ADS2 here, really, the conformal symmetry is broken, and well, there is no large degeneracy of states at low energy, but there is this spectrum which is computed by the Schwarzian. With N equals to 2 supersymmetry is different because this protects some number of states, and so the infrared CFT is a TQFT, which is just a bunch of states with 0 Hamiltonian. It's much simpler than a higher dimensional CFT.
Okay, thank you.
Yes.
So on top of these non-BPS states being cancelled in the Witten index, there are further cancellations for BPS states. Is that the reason why you're finding an optimal Y?
Yes, yes. So
so
maybe I should have stressed this better. Yes, thank you. So yeah, this is precisely the point. So first of all, the non-BPS states cancel completely and do not participate in this index. But then there are extra cancellation, and I will come back to this in a moment. So even among the BPS states, because still these BPS states can have different statistics for the same charges. Some of them could be bosonic and some of them fermionic. So this object is not really, at least on the face of it, is not counting all the BPS states, but is still a bosonic minus fermionic BPS states. So you might still have cancellations. And in fact, you do have. If you take this gas of gravitons in ADS, you can explicitly check. You can list of the operators and you explicitly check that there are cancellations. However, the point is that this difference is the object which is protected by supersymmetry, is very easy to compute. The net number of BPS operators, I mean, it's still protected by supersymmetry, but it's more difficult to compute. And in general, it depends on the coupling.
So the full information is hidden by, I mean, you are getting that by choosing a particular choice of Y.
Yes.
Which will make sure this cancellation doesn't happen, a complex Y.
Yes.
Okay.
I have just an extension of this.
Yes.
So when you choose a Y to make sure that this cancellation doesn't happen in the BPS sector, doesn't it extend to the non-BPS higher states also, non-BPS states?
I mean, the point is that this object here is completely blind to non-BPS operators. I mean, they don't contribute at all. So this object here cannot be used to address non-BPS states.
But for particular value of Y, you're cancelling this -1 to the power f signs that come from there, right? But for other states,
so okay, maybe I should explain this better. So with this argument, let's see. So with this argument, we prove under the assumptions that there is some value of Y for which the phases of the BPS states are all the same. Now, of course, if you are in a given charge sector, this phase here is the same for all BPS states in that charge sector. So the cancellation, in principle, is still coming just from -1 to the f. This argument shows that a given charge sector, if you look at the BPS states, you might think that there are both bosonic and fermionic states, but this argument shows that they all have the same statistics, either bosonic or fermionic. The cancellation within a given charge sector is not due to choosing a specific Y, because all those states will have the same phase from here. It's just that we are making an argument to connect with that argument there and show that in a given charge sector, all the states will be either bosonic or fermionic. So if there were cancellations, they would remain for any value of Y. And so in particular, if you go to non-BPS states, we cannot remedy the cancellation by choosing a different value of Y, because Y commutes with the supercharges, so the pair of states will always have the same flavor charges, and they will always cancel. Okay, good. Okay, good. And by the way, I think that today this is a discussion session. In case that it's still not clear, I can try to explain better later. Okay, so now with this argument, we are more confident that we can try to extract the black hole entropy. And in fact, we can use this very same point of view of looking at the black hole solution as an holographic RG flow to also trying to answer another question, which is the following. So, okay, as I said, we can try to count the states using an index, but which type of index? And in fact, we know of theories in which there are many different indices that one can construct. And essentially, we can use the same argument to also answer this question. Because, as I said, we can take the black hole solution, we look at the fields at infinity, we apply the standard rules of ADS-CFT, and in particular from the fall off of the fields, we can read off whether there are sources that are turned on. And what we find is that the boundary theory is placed in a specific background. Like as I said here, the metric could be S3, but in general, there are also background for all the other background fields that couple to various symmetry of the theory, like background gauge fields that couple to flavor symmetries, or a background gauge field that couple to the R symmetry. And from there, we can read off what is the partition the background in which the boundary theory has to be placed, and this partition function would correspond to some index. And there can be different indices. In particular, we can roughly divide the type of black holes in two classes. So there are BPS Kerr-Neumann black hole, so these are black holes that are rotating, and the black holes in ADS-5 that are described as one example of that. These black holes, on top of that, can have electric charges, possibly can have also magnetic flavor charges. And if you look at what is the boundary theory, you infer that here you have to use a superconformal index. On the other hand, there is another interesting class of black holes. This is BPS black holes with a magnetic charge for the R symmetry. So these black holes sometimes are called the magnetically charged black holes. Sometimes are called the twisted black holes. And the point is that the supersymmetries, the form of the Killing spinors in these black holes is different from the Killing spinors here, because essentially here there is an expectation value for the gauge field that corresponds to the R symmetry that in a sense twists these Killing spinors along the horizon. And so there is a sort of topological twist going on along the horizon of the black hole. And because of that, the index that you have to use in the boundary theory is the so-called topologically twisted index. Yes, and so from here you can read off what is the specific type of index that you have to use, and that will capture the BPS states that are supposed to be dual to the black hole. And as I said, for the specific example that we are discussing, which is black holes in ADS-5, this is the object that we should look at. Yes. Well, there is a third category which has been studied, is being studied in the last year or 2 years, which is called accelerating black holes. These are also called spindles. The horizon is a spindle. Essentially, in these black holes, there is a string of singularity that is attached to the horizon of these black holes. So this string pulls the black hole. For that reason, the black hole is accelerating. And if you look at the boundary theory is placed on a sort of orbifold. So if we were, for instance, in ADS-4, these are a class of examples. So the boundary theory is on S2 times R. And here there is a sort of rotation in this black holes. There are two singular points. This is called a spindle. There is some sort of orbifold singularity here. And these points will be the points where in the bulk there is a string which is attached to the horizon. So this is if you want a third type of black holes in which the Killing spinors are slightly different than for these two classes. And once again, you can use this map to read off how to define a suitable index that will capture these states. It's a little bit more subtle because here there is a singularity. So from the field theory point of view, you have to specify what happens at the singularity. At this point, I don't think it's completely well understood yet. Morally, it's some orbifold singularity, but some data needs to be specified at these points to have a proper definition.
I'd like to
Yes. Question. If you really compute the superconformal index, say for n equals 4 superyoung
Yes.
it shows oscillatory behavior even in the large charge.
Even in the R charge.
Large charge, large Q.
Yes.
But you said that the index only counts the number of states.
Yeah, so the point is that, so as I said, so here, what you're saying is there is an optimal, so if there is an optimal tuning for given charges such that you offset this oscillation in the signs. So essentially, so in this argument, what we are saying is that for every charge sector, all the black hole states will be either fermionic or bosonic, but in general, if the value of your fugacities are general, then as you change the charge sector, this statistic will change. And so you do have oscillatory behavior. And in fact, what the Legendre transform does is precisely, so you fix the charges, what it does is precisely to find what is the phase that is in tune with this oscillatory behavior, such that you cancel that and you get the contribution from that region.
I see, thank you.
Okay. So at this point, we got convinced that we should look at the superconformal index of n equal 4 superior males. So let's look at that. Okay, so what is this object? So we can take a generic four-dimensional n equal 1 superconformal field theory, and we can define this object. So if you go in radial quantization, so generically, this object will depend on two fugacities that or chemical potentials. Let me call them sigma and tau. And the letters that I will be using, of course, will be the same letter that I've been using in the black hole discussion. So this in radial quantization is trace of -1 to the f e to the minus beta q dagger e to the 2 pi I sigma j1 plus r over 2 pi I tau j2 plus r over 2. So what is this? So first of all, this is the trace over the Hilbert space of the theory on S3. We are in radial quantization. This is -1 to the fermion number. This Q is a supercharge, a complex supercharge. And in fact, this supercharge satisfies the following relation. So if you compute Q dagger, this is equal to delta or E. So in radial quantization, this will be the energy, but in fact, it corresponds to the dimension of the operators in flat space. Minus J1, minus J2. J1 and J2 that appear here are the two angular momenta. In fact, there is an SO4 that acts on S3. So J1 and J2 will be the generators of rotation of two planes of the R4 in which S3 is embedded. Minus 3/2 R. So this small r is the superconformal R symmetry. Yes, and for what we discussed, really there is no dependence on beta because only the BPS states contribute to this object here. In fact, this is manifestly positive, so this quantity is bigger or equal to 0, and it is 0 if and only if the states of BPS. So BPS states are the ones for which this quantity is 0, and those are the only ones that contribute to this object here. So from the point of view of flat space, what this object does is to count short representations of the superconformal algebra In other words, we count chiral primaries, which are the generators of not long but short representations of the superconformal algebra. And when we go in radial quantization, this becomes the BPS states. Now, let me just make one observation that will be relevant in the following, which is the following. If we take the n equal 1 superconformal algebra, this algebra is SU2, 2/1. And in particular, the bosonic part is the conformal group, and there is U1R symmetry. And this algebra here has 4 Cartan generators. These Cartan generators are precisely the dimension of the operators, the 2 angular momenta, and the R symmetry. However, the index only depends on 2 fugacities. Now, so we are losing 2. Now, 1 is lost because all the operators that contribute to this index have 0 charge. So if you want, 1 fugacity is irrelevant, so we're not really losing it. But there is another one that we are really losing, which is, if you wish, fugacities for the R symmetry. So, so if you want this object here, which is, once again, looking at BPS operators, is not powerful enough to exactly count the number of BPS operators for given charges, but still is resumming, is blind to one particular charge, and this is what makes it a protected object. If you try to introduce one more fugacity for the missing charge, then this object will not protect it anymore. Okay, another comment that we can make that will be relevant in the following is the following, that well, the angular momentum is quantized, is semi-integer, but the superconformal R charge is not quantized. And in fact, this is related to the dimensions of the operators. The dimension of operators are not, of chiral operators, they are not quantized. And in fact, in these theories, generically, they can be irrational numbers. So this means that this, although it's written in this way, is not really a periodic function of sigma and tau, or if you're using fugacities, so if you introduce p, which is e to the 2 pi I sigma, and q, which is e to the 2 I tau, then the index is not really a single-valued function of the fugacity p and q. It's a multi-valued function, there are different branches, and in fact the physics or the behavior of this index on these different branches can be quite different, and this will be important when we will study limits of this object. Okay, so now for the purpose of these lectures, I'm interested in the n equal 4 theory. So let me just specialize to that. So we are interested in n equal to 4 super Young Mills. So this is if we use n equal 1 notation, this is a theory in which there is a vector multiplet, and there are 3 chiral multiplets, and there is a superpotential. So in fact, in this theory, one can introduce 3 R charges that I will call RA, and in fact, they will correspond to the charges QA that we had in the discussion of the black holes. And these R charges can be chosen such that when we evaluate of this phi b, essentially R1 will give charge 2 to one of them and 0 to the other 2, and so on. Okay, so if you use these R charges here, it turns out that the superconformal R charge, small r, is equal to R1 plus R2 plus R3 divided by 3. And besides, we can introduce some flavor charges that I will call small q, 1, 2. And these can be defined as R1 or R2 minus R3 divided by 2. And so if you use these charges small q and this big R, you can check that all the fields in the theory have integer charges. And so this choice is convenient because then the index will be a single-valued function of all the fugacities, because all fields, all operators will have integer charges. So this index now will be function not just of 2 variables, But because of the presence of these two symmetries that from the point of view of an n equal 1 subalgebra are essentially flavor symmetries, there are two more fugacities that we can introduce, y1 and y2. So it will be this object here. So P to the J1 plus. So we'll also make a smaller definition of the fugacities in such a way that here, instead of having the superconformal Arrow charge, we have this R3. And then Y1 to the Q1 and Y2 to the Q2. Okay. So this is the object that we will be studying. Now, it turns out that it is convenient in writing the formulae to introduce a if you want, a fifth fugacity, which is not an independent variable, it's just a function of the other ones, and this will be convenient to write our formulae. So one introduce an auxiliary y3 such that PQ is equal to y1, y2, y3. So this is an auxiliary variable, and it's convenient because then there will be some SU3 symmetry that acts on these variables, and the formula will be more symmetric. Okay, so how do we compute this object here? So let me just very quickly say how we do that. And the point is that, so in this theory, there is a continuous deformation. There is a marginal direction, which is the coupling. And the index does not depend on this direction. So we can continuously push the theory to weak coupling. And in fact, we can go in the free theory. And then we can compute this index in the free theory. And this index will not depend on the coupling, so it will be the same at strong coupling. So how do we compute this index in the free theory? So the first step is to look at the so-called BPS letters. So we look at simple fields that are BPS. Okay, these will not be operators; they will be simple fields. And one can take just the fields of n equal 4 superior Mills and draw a table. I will not do it, but essentially, so for instance, one field will be the scalars in the vector multiplet, and one can list the charges of these fields. For instance, you will have dimension 1. One can look at what are the left and right angular momenta. These are scalars, so the charges are 0. One can look at the superconformal charge, which is 2/3. And moreover, with respect to these SU3 flavor symmetries, they form a triplet, so there are 3 of them. And so one can assign monomials to them. So for instance, for these guys here, the monomials will be y1, y2, y3. So essentially, you just have to evaluate, given the charges, what is the monomial that you obtain from here. And there is also a sign. In this case, these are scalars, so it will be a plus. So for each of the BPS letters, you write down this object here. Well, it turns out that you can also consider derivatives. And in fact, you can have a generic number of derivatives. Now, only just 2 of the 4 derivatives. So this will be the plus dot or the minus plus dot. And you can list the charges of these derivatives. And there are monomials that you associate with them, P and Q. In fact, these derivatives, they form descendants. So essentially, from the point of view of radial quantization, they change the momentum of the states. And there is one free equation of motion that you have to take into account. Anyway, you collect this data, and you form what is called the single letter index. So essentially, this is the index, but not for the full theory, just for simple fields. And if you collect all the monomials here, you get the following expression. So the first piece comes from these fields here. Then there are other fields that have not listed here. And as promised, notice that there is a nice permutation symmetry between 1, 2, and 3 if you use this auxiliary variable. But then we can also act with a generic number of derivatives. And so if we sum the contribution of all generic number of p and generic number of q that can act, we get this denominator. So if you expand these denominators, you get that there is an arbitrary number of p and q that can be attached in front of these monomials. Okay, so these are just the simple fields. But then you really want to construct operators, which are product of simple fields. And so you need to count all possible products, in fact, unordered products of operators. So you want to count all unordered products of letters. And this is done by the so-called platistic exponential. So in other words, if you have your single letter index, and let me assume that there is for simplicity, that there is a single fugacity that they call x. So this f of x will be a collection of monomials. So we'll have the following form. And we'll have the property that f of 0 is equal to 0. So there is no term of x to the 0. Then the platistic exponential is defined in the following way. So this is, if you want a functional transform, is given by the exponential of the sum from n to 1 to infinity of 1 over n, then f of x to the n. So for instance, so let me consider the simplest example that we can think of. Suppose that we have a single letter. So this will be the platistic exponential of x. Then when you substitute in here, this gives you the Taylor expansion of the logarithm minus the logarithm of 1 minus x. But you have to take the exponential. So this gives you 1 over 1 minus x. And then if you expand this geometric series, this is precisely 1 plus x squared, etc. And in fact, this single letter means that we have a single field phi of charge 1. And what are the unordered products that we can form? Well, of course, there is the identity, there is phi squared, phi cubed, and so on. So, okay, this is the simplest example. It works. And of course, you can try to some other example, and you can see that, in fact, this does the correct counting. Now, of course, we have to take into account that the fields also have gauge charges. So when we do this counting of the letters, we should also attach fugacities for the gauge charges. And in n equal 4 superior mass, all the fields are in the adjoint representation. So one should use the adjoint character. This is a sum over all roots of the group, z to the alpha, whereby this writing the alpha, I really mean that there are fugacities for the Cartan of the gauge group, and I'm taking a product from 1 to the rank of the gauge group, zj to the alpha j, where these alpha j are the components of the root. So if we do that, what we are doing is that counting all possible products of fields. In general, this will not be gauge invariant operators, so we need to select the gauge invariant operators. And to select the gauge invariants, we perform an integral of the gauge group. that we can write in terms of essentially integral over the maximal torus and a van der Monde determinant. So this will be 1 over the Weil group of G, an integral over the maximal torus. So this Rk is the rank of the gauge group, a product for J from 1 to the rank of the gauge group, this is J over 2 pi I Zj, and then the van der Monde determinant. Okay, so putting everything together, what you attain is the following. So one expression for the index, to which perhaps we will come back to the at the end, is the following. So for the special case that the gauge group is UN, in fact, it turns out that the adjoint, well, if you want the fundamental character, you can have a matrix U, which is a matrix of UN. The fundamental character is just the trace of this matrix, and then the adjoint character is the trace of U minus 1, just because the adjoint is the product of the fundamental and the anti-fundamental. And so you can write down the index of the UN theory as an integral over the whole UN, du, where U is a matrix of UN, and then this platistic exponential so f, you have to use the function that I wrote before, and that was here that I just cancelled, that depends on the 4 fugacities. And then we have to put the adjoint character. So as promised, this gives us an exact formula for the index. Now, if more generally the gauge group is not UN, then we cannot use this trick, but we can more simply work in this basis of the Cartans. And in fact, it turns out that this platistic exponential can be worked out with some algebra. And one can write the result. It turns out that the results depend on 2 special functions. Yes, so for the special case of UN, so here I'm writing the character of UN is just, okay, take the matrix of UN and take the trace. So this is the trace in the fundamental representation. So this is the character of the fundamental. And then we use the adjoint of UN is the product of the fundamental and the anti-fundamental. And so the character of a product is the product of the characters. So use that to see that this is the character of the adjoint of UN. But it only works for UN. Not for SUN, for instance. Yes, so we can do so in the general case, we can get the following formula. So we have to use 2 special functions. One is called the Kupo-Kammer, which essentially, well, okay, I mean, it's this function here. And the other one is called the elliptic gamma function, which is defined as some infinite product. Okay, so these are some special functions. And with this function, we can finally write a final formula for the index, which is the following. So there is some contribution from the Cartans. And these contributions are here. This is the dimension of the Weil group. Then there is this integral over the maximal torus. And then there is some product of these gamma functions, essentially by computing this statistic exponential, one gets one gamma function for each chiral multiplet, and then one gets something for the vector multiplet. So for each chiral multiplet, so there are 3 of them, because there are in n equal 1 notation, there are 3 chiral multiplets. There is a product over all the roots, all the weights of the adjoint representation. And then there is this gamma function. And here the gamma function is written in terms of fugacities. Here I write it as a function of chemical potentials. So let me put a tilde here. So it's the same function, but here you have to use P is 2 to 2 pi I sigma, Q is to 2 pi I tau, and Z is 2 to the 2 pi, E to the 2 pi of what is here. So this is the contribution from the chiral multiplets, and then there is a contribution for the vector multiplet, which turns out to be another elliptic gamma function, but in the denominator. Okay, so as promised, there is an exact formula for this index. And our task will be to try to understand what is the behavior of this formula. So of course, this is an exact formula, but still there is an integral to do. And in particular, as you increase n, the dimension of this integral becomes larger and larger. So it's not completely obvious to understand what is the behavior of this integral at large n. Okay, and our task will be to understand that. So let me just finish with one remark, which is something that we already mentioned, but is the following. So this object here was computed in the free theory. Okay, we literally go to the free theory, we list the free BPS fields, and then we form free BPS operators by just taking products, gauge invariant products of these letters. Now, when we go to the interacting theory, things change in the sense that generically, BPS operators stop being BPS. So in the interacting theory, the number of BPS operators is smaller. And this is easy to understand from the point of view of the CFT, because what you can have in a CFT when we turn on some deformation is that short representations combine into some long representation, but then long representations are not protected anymore, they can get an anomalous dimension. And the same happens from the point of view of BPS states. So you can have pairs of states that are BPS in the free theory, but then you turn on the interactions and they pair and they become non-BPS. They acquire some extra dimension, some extra energy. And in fact, counting the BPS operators in the interacting theory, it's a difficult problem. In principle, a strong coupling is very difficult. There are some conjectures that perhaps only the one loop, well, this problem is exactly one loop, but it's conjectural. However, we don't see all this problem in the index. In the index, there is a difference between bosonic and fermionic BPS operators. And for that reason, the index is the same in the free and the interacting theory. But the actual net number of operators will be very different. That said, we already commented on the fact that when we go to large n, and if the theory is holographic and the density of states is dominated by a large black hole, then in fact, at leading order, there should not be cancellations, and we expect all the BPS, most of the BPS operators to have the same statistics and not to disappear even when we turn on the interactions. Okay, and with this remark, I will conclude.
Okay, so I think we have time to take several questions. Are there any questions?
So just a simple question. So this formula also works out in the simplest of setting, which is just U1. Could this formula be just reduced? I mean, this general formula that you wrote for a generic UN group, can I do it for abelian U1 theory?
Yes. So that is much easier because in U1, so okay, first of all, the U1 theory is free. Moreover, all the operators are gauge invariant because the fields are in the adjoint. So you don't have to do this integral. And okay, Okay, I don't remember the exact, so let's see. So essentially what survives is this prefactor here. In fact, these are as many as the Cartans. So there will be one factor of this. There is no Weil group. And here in these weights, you only take the singlet in the joint representation. So there will be these 3 factors here. So I believe that for U1 is this Pochhammer, and these 3 gamma functions.
I see. Okay, thank you.
So you emphasize that out of this, all the interaction effect is gone. Am I right?
Say again?
So there is no coupling dependence, you emphasized?
On the index, yes.
Right. So, but usually why we want the exact result is just because we want to pick up some strong coupling effect.
Yes.
So is there any way to, to extract any of the interaction effect out of this calculation?
Not in this quantity. As long as we work with the index is independent of the coupling.
Okay. So then the yesterday,
yes.
Also, you also said that if we complexify and with a complex temperature,
yes,
then we do have a supersymmetry. Is there any way to utilize some supersymmetry to calculate this gravitational integral exactly, so that we do have a temperature effect and also coupling?
As I said, as long as we work with supersymmetry, so there was a supersymmetric temperature, this beta that becomes complex.
Yes.
But really, for the quantities that we look at, there is no dependence on beta. Because the grand canonical partition function that I computed at the end, that was, so this what I called I sugra, that was this I pi n squared delta 1, delta 2, delta 3 divided by tau sigma. So you see, these variables will eventually be the same variables in field theory, but there is no beta. And in fact, perhaps this was not immediately obvious from gravity, but it matches the fact in field theory that you can introduce this fugacity for the supersymmetric Hamiltonian, but since only the black holes, the BPS states contribute, there is no dependence on it. On the other hand, as I said, in some sense, you might regard this 1 over imaginary of tau, or sigma, I'm taking tau equal to sigma, as a sort of supersymmetric temperature. More or less in the same way as it happens in 2 dimensions. So in 2 dimensions, you have a torus. So if you take a 2-dimensional CFT, and in this torus, so this is tau, and so the imaginary part of tau is beta, is the length of the circle, is the length of the temporal circle. And in fact, the real part of tau is given by this length. It tells you, so when you go around the temporal circle, how much you twist the spatial circle. So this is related to angular momentum, but you can regard the imaginary part of tau as this is the temperature. And there is something similar in 4 dimensions, because you have S3 times S1, and there are 2 lengths here, because this length of the S1 and the size of the S3, and you can regard the imaginary parts of tau and sigma as the sizes of these 2. So in fact, this is the reason why this imaginary part, 1 over the imaginary part, plays the roles of a supersymmetric temperature somehow, while the real parts will describe how you twist the S3 as you go around the S1. So it's more related to the angular momentum. And if you regard this as a supersymmetric temperature, this comment that I learned from Seok, that qualitatively the behavior is similar, perhaps, but just qualitatively, I'm not pushing it more. Schwarzschild black holes in ADS5, but it was just qualitative level. I mean, it's not precise.
Thank you.
Okay. Other questions? Okay. Otherwise, let's thank the speaker again. And is there any announcement for lunch or dinner? Yes. Okay.
The black holes due to the super conformal theory is consists of bosonic, either all the bosonic or fermionic.
Yes. Well, this is what seems to come from this argument. Now, I mean, it will be nice to check that.
How can I understand this?
But I think that so if you take the Schwarzian approach that Tuliacci described, so that one really captures the near horizon. So of course that is a bulk argument. So I don't know how to do it from the field theory point of view. From the bulk, you can say one way to isolate, to define what is a black hole state as opposed to a graviton state is, okay, go to the near horizon and just use a description of the near horizon. Now, in the near horizon, you can use this super Schwarzian description, and there they can explicitly see that, in fact, first of all, there are supersymmetric ground states of this super Schwarzian, which are propagated by supersymmetry, and moreover, they all have the same statistics. So, yeah, with that approach, you can check that.
I just want to repeat myself what I learned from your lecture in the last lecture. So at the time we started with some supersymmetric solutions. Yes. And we had three requirements: extremity and
Yeah, yeah, yeah. It's working. It's okay. Yeah. Okay. Yeah, yeah, I have. It's okay. Thank you. Is everything okay? Is everything okay with the Zoom? Yeah.
All right, I think we need to start the afternoon sessions. And Gustavo will continue his lectures on solvable models of quantum black holes. So please.
Okay, thank you. um, sorry. Yeah. Okay, so in this lecture I will change topics a little bit and discuss the another topic related to the chaotic nature of black holes, which is the relation with random matrices, random matrix universality. But let me begin by some recap of yesterday, since especially since in the last couple of slides I have to go a little fast. So what we did was to solve exactly JT gravity coupled to matter. JT gravity coupled to matter has two parameters that suppress quantum gravity effects. The first one is this S naught, which we always take to be large. This suppresses, on one hand, topology change, which will be the topic of this lecture, but it also suppresses interaction between the matter and the JT mode that we don't know how to solve. And this S naught was always taken to be large. But something special in JT gravity compared to higher dimensions is that now there is a second gravitational coupling, which is this combination of C times T. C is this scale that appears at which the conformal symmetry is broken by the boundary conditions, and T can be the temperature or also something that has units of energy. And we solve the theory when this gravitational coupling C times T is finite. Oh, sorry, actually the coupling is the inverse of C times T. So when C times T is large, the quantum gravity corrections are small, and when CT is small, quantum gravity corrections are large. So what I showed in the second lecture was the solution in this regime. This is not a complete theory of quantum black holes consistent with holography. For example, the spectrum in this regime is continuous. That means that it has infinite entropy. That's not what we expect from holography. And in these lectures, we will see the role that space-time wormholes play in addressing some aspects of this problem in some simpler toy models than the ones that appear from higher dimensional setups. Before I do that, since I went a little bit fast in last lecture, let me, well, if there is any question about the previous two lectures, before I slightly focus on other stuff, feel free to ask now, perhaps. Is there any question? Yeah.
So, to which extent is correct to assume that this S naught is connected to the entropy of the full entropy, the full geometry black hole? I mean, I'm expecting this IDS2 as appearing in the near horizon of a black hole.
Yeah.
Is S not connected to the entropy of the black hole as seen from the full geometry?
Yeah. So S naught is a parameter in the throat that you need to compute from the from the ADS2 point of view, it's a parameter of the theory, but when you embed ADS2 in a bigger black hole, then it tells you what S naught should be.
So should this hold also even as subleading corrections? I should expect that they come also in terms of this S naught?
Yeah, for example, in the Reister-Nordstrom case, the gravity approximation near the horizon is accurate when the charge is large in units of Planck length. Then this S naught will have an expansion at large charges. That to leading order it will be the extremal area, and to subleading orders it will be some more complicated function of the charges.
Okay, thanks.
Yeah. And the same applies to computing this parameter C. Any other question? Okay. Yes. So I mentioned that the problem that this theory has is that it has a continuous spectrum. Just to remind you, this is the density of states of essentially JT gravity also coupled to matter as long as you absorb some extra coefficients in S naught. And this is definitely not the sum of delta functions, which would be a spectrum with finite entropy that is discrete. This is compatible in some sense with the fact that the canonical entropy, meaning at finite temperature, if we compute the entropy, it does satisfy the Bekenstein-Hawking relation, at least at large energies. So the canonical entropy is fine, but what it loses is the meaning of the Bekenstein-Hawking entropy as an interpretation of counting states. Because any type of counting that you try to make in this system will just give you infinite. So in that sense, this only works if strictly S0 is equal to infinity. But this is not the way we expect holography to work. We expect the black hole Hilbert space to have a finite dimension, and this is at the heart of all the type of information paradox. For example, if the number of states of the black hole is infinite, then there is no contradiction. Then the radiation of the entropy of the radiation can go indefinitely. There is not really any contradiction with that. So the motivation for this lecture is to try to understand from gravity how to go beyond this infinite S0 limit and try to see some aspects of the finite entropy spectrum. Yeah. Yeah. Yeah, that's what I mean. That in the canonical is fine, but in the perhaps in the macrocanonical, we expect that in general you can define some kind of energy window around some chosen energy, and that the Hawking entropy, the Bekenstein-Hawking entropy is counting states in that energy. But if you try to do this, you will always get an infinite number of states. If you just count states in the macrocanonical, of course, if you put factors like e to the minus beta e or something that makes it that somehow coarse grains over the. No, but that's not the. I think that's not the right calculation to do, because the fact that this is continuous means that you have an infinite number of states in any energy window.
There's no way of thinking of it as a smoothing out of this delta function.
Well, that's the point. Like, you want to interpret it as a smoothing out, but at this level, it's hard to figure out perturbatively what corrections, where would corrections come from that would correct this and turn it into a delta function. And we want to see where that comes from gravity. So yeah, I agree. That's the.
Can I also ask a related question?
Yeah.
Because normally we expect that if you include all the subleading quantum gravity corrections, we might be able to see discreteness. But you're saying it's continuous here because of the Stanford and Witten's argument that one loop results are exact. So we should regard it as exactly continuous thing.
Yeah.
Okay.
Yeah, so perturbative effects around the black hole saddle don't solve the discontinuity issue. Yeah, so that's something very, sorry, quick comment. That's something very special about 2 dimensions or also in 3 dimensions where you can actually do the calculation of the perturbative corrections that would not be available in 4 or higher dimensions. But yeah, so. Yeah, that depends where the black hole is sitting inside. If the black hole is sitting in flat space and there is some particle with that satisfies the weak gravity conjecture, then you compute the partition function, and so the contribution from then you will get some imaginary contribution, and you will interpret that as decay. Yeah, but I'm having in mind perhaps for this motivation that the ADS2 throat is sitting inside the bigger ADS, and the black hole is stable to make this, so that one can talk about these energy levels in a more precise way. Yeah, some toy models of what you're saying in 2D would be to couple ADS2 with some bath. Sometimes people pick a flat space, 2-dimensional flat space, for example. That would be a toy model of. But then these eigenstates somehow get diffused because you have to couple that to the bath and find some common eigenstates of the whole system. So I'm thinking of the simplest case where you take ADS2, it's sitting inside some bigger ADS, everything is stable. Yeah. Any other question? Okay. The fact that the spectrum is incompatible with finite entropy is related to the information paradox that raised by Maldacena in 2001. The original version of this paradox was proposed for 2-point functions. Then the 2-point function, you can write it this way if you have a system with a discrete spectrum. At early times, you expect this to be of order e to the S0, just because, well, the matrix elements are, according to ETH, they are suppressed in the entropy in a way that when you take the square, they go as e to the minus s, and then you have a sum over n and m, two sets of states, and then this gives you something of order e to the s naught. But when you take late times, this collapses this double sum to a sum over just one energy eigenstates. So this means that at late times, the two-point function should be of order 1 for a system with a discrete spectrum. And instead, we see that if we compute the two-point function at late times, it goes to 0. So there should be some effect at late times that stops this decay. And we see that this should be a non-perturbative effect because, okay, if you normalize the two-point function such that it's 1 at early times, then it will be exponentially suppressed in S naught at late times. So this is an null manifestation. This is only a problem if S naught is infinity. Now, according to ETH, we expect the operator matrix elements to be smooth functions of energies. So it is reasonable to formulate Maldasena's paradox for the spectral form factor instead. And this was introduced in the paper of Kotler and a lot of other authors, 8, 9, I don't remember, in 2000. Oh, sorry, actually it was 2016, not 18. It's called Black Hole and Random Matrices, I think. So this is just the product of two partition functions that depend on beta plus IT and beta minus IT. And this is the way that this quantity looks like if you expand in energy eigenstates. And you can see that this is essentially the same as a two-point function, but where I stripped off the matrix elements of the operator. So this quantity is, in a sense, more universal than the two-point function because I don't need to make a choice about the matter. So this goes similarly to the previous case. It's of order e to the 2s at early times because I have two sums, and at early times the two sums are unconstrained. But then at late times, the oscillatory phases from this Lorentzian evolution will set En to be equal to Em. And then I have a single sum over energies. So it expected that at late times, this quantity is exponential by a single power of e to the s. Roughly, this is the behavior expected for a chaotic Hamiltonian. So first, it should decay. This is the Schwarzschild part that we computed in the first two lectures. But then at some point, this has to saturate, perhaps with very large fluctuations, around the value that is exponentially smaller than the starting point by a factor of e to the s naught. And as I said, this is a more universal quantity. From the gravity path integral, the spectral form factor is computed by an integration over geometries with two boundaries of this complexified length, beta plus IT and beta minus IT. And here I write it in this way. So C grav is the gravitational path integral with the two boundaries specified by these two lengths. And I'm not writing it as a product because, as some of you probably saw, some effects coming from changing topology can actually give a non-connected contribution. We'll come back to that later. But in principle, you need to integrate over anything that can happen between these two boundaries. Yes, so it's factorized by definition if you assume that the black hole is described by a quantum system that is unique. Here, this is the gravitational prescription to compute it, and that should come out of gravity. It's not something that you can put by hand. No, the way I see it is that there is a definition that is in quantum mechanics, and there is a definition in gravity. And there is a property that, like you said, that is a product of two things in quantum mechanics that is not evident in gravity. That if you have two boundaries, the result will factorize. Yeah. Okay. Okay. Including only the black hole saddle that we used in the previous two lectures gives a spectral form factor that is the product of two partition functions. So this would be the case where, in principle, you would say, okay, this is factorized, this looks like quantum mechanics, so there is no problem. But then you compute it, and you get this function. So this is evaluating the product of the Schwarzschild partition function. And you see that at late times, it decays as a power law of 1 over t cubed. And this is the same power law that we found in the late time behavior of correlators. And it can be traced to the fact that the spectrum is continuous. So this 1 over t to t cubed is this original decay. So instead of working with JT gravity coupled to matter that arises from near extremal black holes, we will consider a toy model, and this will follow the presentation of Sad, Schenker, and Stanford. And we will study pure JT gravity. And let me stress, based on what I said in the first two lectures, that this is not really a toy model because of being two-dimensional. Instead, it is a toy model because it has no matter. In some sense, going to higher dimensions or trying to extend what I'm going to say to theories of JT gravity with matter is equally difficult as some sense as studying higher dimensional cases. And we can generalize the previous question about the spectral form factor and ask whether the gravitational path integral with multiple n boundaries is equal to the product of the respective partition functions of the quantum system. Yeah. Yeah, that debate is not important in 2 dimensions because in 2 dimensions you can, well, that will be the goal of the talk, to explain what the dual of pure gravity is in 2 dimensions. If you try to play the same games in 3 dimensions, you run into some issues that has not been really solved. So in a sense, this is like also a toy model of pure 3D gravity, and in this case, it will be solvable. Okay. So Sad, Schenker, and Stanford in 2019 proposed the following resolution of this version of the information paradox, which is to include the sum over topologies in the path integral. If S naught is finite, which is the only case where this is really paradoxical, then there is nothing suppressing topology changes, and we should include all these contributions in the gravitational path integral. And this is something very difficult to compute if you have JT coupled to matter, but that's why they restrict to pure JT. And the upshot of SSS is that this theory is dual to a random matrix model in a double scaling limit that I will introduce in the next slides. And they were able to prove this perturbatively in the topological expansion, meaning order by order in this expansion where we add handles to the geometry. But some questions involving non-perturbative effects will remain, that we'll mention later. And let me, just to motivate another case, well, you could ask, how do we know that we are supposed to include topology change in the gravitational path integral? And just to mention a very simple toy model is this, the confinement phase transition in n equals 4, which is dual to the Hawking phase transition between thermal ADS and the ADS black hole. They definitely have different topologies. One is a circle times a disk. The other one is the plane times S3. And at least this is the simplest example, perhaps, that shows that at least from the dual quantum field theory, it indicates that including some over topologies is important. But again, the case we will consider is a little even more drastic than this example. It's just as an illustration of a case where summing over topologies is important. Okay, so we will refer to these configurations as space-time wormholes. For example, in the case in the right, you have 2 boundaries, and this is called a wormhole because it connects both boundaries. And these are wormholes in space and time. So they are called space-time wormholes. And this is different from the wormholes we encountered in the first lecture, which connect different regions of space. And the interpretation of the wormholes in the first lecture is that they geometrize the entanglement between the two-sided, the dual of these two-sided black holes, or the 2 quantum mechanical systems. They're in this thermofield, for example, in that case, they're in the thermofield double state, which has a large pattern of entanglement, and that's related to these wormholes. But these are different type of wormholes. They are space-time wormholes, and so we want to see what do they do. We will see after solving the theory in this toy model that is related to the indeterminacy of coupling constants of the dual quantum mechanics. And this is where the random matrix model emerges. It will be the random matrix will be a random Hamiltonian, which is the dual of this pure JT black holes. Is there any question?
I have a question.
Yeah.
The topological expansion, is it convergence series?
No.
Or asymptotic series?
Yeah, that's what I mean about the non-perturbative ones being not really. Yeah, there are some questions about that. Yeah. Okay. So the purpose of this talk will be to solve pure JT gravity, including the sum over topologies or the sum over spectrum wormholes. And thanks to this topological term in the action that is proportional to the Euler characteristic, and thanks also to the fact that the topologies in 2 dimensions are so simple, namely just adding handles, that's all you can do, and a handle is like a wormhole. The gravitational partition function can be expanded as a sum over wormholes or a sum over handles from 0 to infinity. And each contribution will be a path integral with a fixed topology, fixed number of boundaries, and it will have a universal weight as this power of e to the s naught, where this prefactor is just the Euler characteristic with a surface with g handles and n boundaries. And the prescription that we will use to solve this theory will be to still integrate out the dilaton first. This will restrict us to hyperbolic metrics of uniform curvature. But now there will be a very non-trivial modular space of these hyperbolic spaces for a given topology and boundary conditions. And we will have to deal with this complication to compute it. So the goal of what I will describe next is, can we find an exact answer for this CGN that we can use to compute the full gravitational path integral? Okay, so having fixed, again, as I said, you fix the number of boundaries. We fix the number of handles because we want to compute the individual CGN, and we integrate out the dilaton. So imagine first, to simplify the model, that we consider geodesic boundaries as opposed to the boundaries we've been studying in the past 2 lectures. These are boundaries where that have a vanishing extrinsic curvature. That's the condition for them being a geodesic. And in particular, they are simple because they don't have boundary modes. The Schwarzschild mode does not appear there. And then the original path integral gets reduced to an integral over hyperbolic metrics because the integral over the dilaton will localize over metrics that have r plus 2 equals 0. So this reduces to an integration over the moduli space of hyperbolic surfaces with n geodesic boundaries of length b1 to bn. These are the length of each of these geodesics. And we will denote that by mgn as a function of b. And this moduli space is very complicated, and it has dimension. It has this dimension. It's 6g minus 6 plus 2n. So the more wormholes we add, the bigger this moduli space is. The measure of integration over this moduli space, one can derive it from the gravity path integral, and it's the Val-Peterson one that I will introduce in the next slide. And then the path integral of pure JT gravity over these surfaces is given by the Val-Peterson volumes, which is the integral over moduli space with this particular volume form. And that's the answer for the JT path integral on this type of geometries. Now, I'm not going to go through this derivation. I'm just telling you, I'm going to tell you only what the Val-Peterson measure is. But a thorough discussion of how to show this, starting from the JT path integral, can be found in a paper by Stanford and Witten. But I'm not going to have time to go through this derivation. But it's basically doing a more careful reduction of how we go over the integral of metrics to an integral over the coordinates over the moduli space and reading off the measure from there. So it's like a one-loop calculation. Okay. So this is the Val-Peterson volume. So we can decompose any hyperbolic surface with genus G into a set of pair of pants. This is a pair of pants. And such a decomposition will have 3G minus 3 plus n connecting tubes. This is, I will leave it as an exercise to check that this number is correct. So we take a surface, we cut it along geodesics and decompose it in pair of pants, and then we denote the lengths and the twist of each internal connection by b and tau. And this is called the Fenchel-Nielsen coordinates. And b, this b tilde, and I'm calling it b tilde to emphasize that it's an internal geodesic boundary, geodesic from cutting the surface, and not as opposed to b, which is an external geodesic length. So the modular space is described by the weight of glue, cutting and gluing these geometries, and that's described by the length of each of these internal boundaries, plus the twist, which is the freedom to rotate one boundary with respect to another when we glue them. Then this modular space is described by these b tau coordinates. In these coordinates, the Weil-Peterson measure is given by this simple formula. So this, well, this is written in form language. So this is the symplectic form omega, and then if you want to compute the measure, you just compute the power of omega that has the right dimensions. So one way to write it is to write the integral as the exponential of this symplectic form. And then what's called the Weil-Peterson measure is whatever you get from picking the form with the right dimension in this exponential. And that's what mathematicians call the volume of this, the Weil-Peterson volume of this modular space. And again, the non-trivial calculation is to show that the gravity path integral reduces to precisely this measure. Okay. Is there any question about this? Yeah. Why do I need to exponentiate it? Yes?
Right.
No, I don't need to. I'm just doing it. This is just a convenient way to write it, because when you exponentiate it, all I mean is that you are going to pick the power of omega that has the right dimension for the integral to be non-zero.
I see.
So I'm just writing it in a way that it's independent of the dimension of the modular space.
But you expand this exponential, then you will get only one omega. Only one omega will contribute to the integral. No?
Yeah, but that one omega depends on the dimension. So then I will have to write a different formula.
But the omega has the right dimension. It's a sum. Oh, sorry. Okay. It's all right. Thank you.
Is it okay?
It's okay. Thank you.
Okay.
Okay, sorry.
Yeah, thank you. Any other question? Okay. So this Weil-Peterson measure we wrote before is very simple, but nevertheless there is an important issue, which is the mapping class group. These are large diffeomorphisms, meaning that they are not connected to the identity, that identify surfaces with different functional insert coordinates. So you could have two surfaces that are cut in different ways, but there is a very non-trivial large diffeomorphism that identify them, and this is called the mapping class group. So even though the measure looks so simple in these b tau coordinates, the region of integration to make sure that you're not overcounting has a very difficult, or is very difficult to identify. And this is the main complication. So you want to avoid overcounting and integrate over only by the fundamental domain. If you ignore this issue of the mapping class group, the modular space is called the Teichmuller space. Computing volumes, here it's easy, they're all infinite. So it's not really a very well-defined theory. It's definitely not the theory of gravity, because in gravity you really want to mod out by this mapping class group. You don't want to consider different geometries related by diffeomorphisms to be different. But in some applications to 3D gravity, thinking about Teichmuller space is useful, so I wanted to just mention it. Perhaps the simplest example of what I wouldn't call it the mapping class group, but just an example where the domain of integration is smaller than what you expect is when you integrate over the twist. So this is one of these internal boundaries. Then the integral over the twist is only done over twist between 0 and b, because once you did a full turn, then you go back to the same surface. So whenever you integrate over twist, you do it in this finite range. So this is just a small example of simple one. So okay, so having this in mind, let me go back to JT with the holographic boundaries and construct the solution. So let's start with the simplest case, just as we already saw it in the first two lectures, which is the disk. So the disk is also called the cigar, is the original black hole with no non-trivial topology. And again, this is given by the Schwarzschild partition function that I wrote many times. For the disk, the Euler characteristic is 1, so all the contributions from the disk are multiplied by a factor of e to the s naught. So they're all large. And this also gives the leading contribution to the path integral with multiple boundaries. So if we do a path integral with multiple boundaries to leading order, it will be a disconnected product of one disk for each of the boundaries, and this will grow. This will have the largest grow with e to the s naught, as e to the s naught to the power of the number of boundaries. The second example, that is the first non-trivial one, is the cylinder. And this is the picture that I drew before. And this is the leading order correction to this spectral and form factor calculation. So if you want to compute the gravity path integral between the two boundaries, well, the leading order is the disconnected one that I wrote before, but the cylinder is the first subleading correction to it. And in particular, is independent of S naught because the Euler characteristic of a cylinder is 0. So while the disconnected part grows as e to the 2s naught, the cylinder will be of order 1. After integrating out the dilaton and the metric, the only moduli other than the boundary curves are the size and twist of the geodesic in the middle. So if I have a cylinder and I write the hyperbolic metric, it will have this form. And in particular, it will have a geodesic somewhere in between the two boundaries. And here I labeled it by B and tau. And the red line just indicates that tau is a twist when we glue these two halves. And again, in this case, because of to not overcount, we want to integrate tau from 0 to b. Just to be more specific, in this equation is the precise metric of this space, depending on b, which is here, and depending on tau, which is here. So the amplitude in the cylinder can be computed by gluing these two trumpets, which are these half cylinders, which interpolate between this holographic boundary with renormalized length beta and this geodesic boundary with length b. And in the middle, we integrate with the Weil-Peterson measure, which in this case is just, it's always, in this particular case, which is two-dimensional, is dB d tau, and with this subtlety about the range of tau. The remaining thing to compute is the path integral of the boundary graviton on each of the trumpets. And this I mentioned briefly. I'm not going to go over the calculation, but I mentioned briefly by the end of the yesterday's second lecture that this can be computed following similar techniques as what I described for the disk. And this is the answer, which depends on the renormalized length beta at the holographic boundary and the length of the geodesic b. And the way to derive it is similar. You need to derive what the action of this boundary mode is. It will not be the Schwarzschild that I wrote before. It will be something slightly different. And then you can compute the path integral, and this is what you get. And it's also one loop exact for similar reasons that the disk partition function was one loop exact, but just a different theory. Okay, since the trumpets are independent of the twist is just about something about how we glue it. This toy model version of the mapping class group implies that the integral over tau is just a factor of b. Yeah. You mean why this is independent of tau? Why the trumpet partition function is?
Why is the gluing point as big a space as like the Schwarzian configurations? Like they are also diffeomorphisms of a circle kind of thingy, right? How do I?
Sorry, I don't understand the question.
So the asymptotic boundary had like so many configurations, which was counted by some Schwarzian measure.
Yeah.
Right. And similarly, the space where these things are glued, doesn't that also have a Schwarzian worth of?
No, it doesn't have a Schwarzian because of the boundary condition. So because it's a geodesic, so in the Euclidean derivation of the Schwarzian comes from the Gibbons-Hawking term. I mentioned it briefly in the first lecture. So you need to evaluate the extrinsic curvature at the boundary. That gives you a Schwarzian. But in this boundary, the extrinsic curvature is 0 because that's the condition that is a geodesic.
What does that mean? Like putting a geodesic condition, like
that k is equal to 0 there. That's equivalent. Yeah. And then there is no boundary mode there. Yeah.
But physically, what does that mean? Like putting a geodesic as the gluing part, like.
physics.
Why not put a K and sum it like that? Like, what's the difference?
Why not put what? You mean an arbitrary value of K?
Why not put a Gibbons-Hawking term and count all the ways these two surfaces could have?
I mean, I'm just doing the calculation in the simplest way I could do it. Maybe there is a more complicated way, but in the simplest way, you first integrate out the dilaton, you have a hyperbolic metric on the cylinder, and then you know that there is always a geodesic. You can show it. All the hyperbolic metrics have geodesics that are homologous to the boundary. In this case, there is just one in the middle. And then I'm just using that geodesic to cut the geometry and separate the path integral in two, just because that's the one that I know how to do. If you want to cut this in two different, more complicated ways, then computing that will be more complicated. But
Asking is this choice we make on the theory, or like would are these calculations for some mathematical reason identical, or like
for some what?
Whatever the mathematical reason, like you said, is it a complicated way to do it, or is it a choice we make? That
I made the choice of computing it in the simplest way I could, which is to cut it in a geodesic, because then I don't have to worry about boundary modes at that boundary.
Okay. Thanks.
Yeah. 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 B is the proper length is the geodesic length of this geodesic boundary. Why is well, you could ask the same about the disk. The disk is also proportional to 1 over beta. You mean why the yes? So the the action. Let's say you have the disk, just the disk. Then the action is the integral of the Schwarzschild. Okay. If you evaluate the Schwarzschild on the solution that corresponds to the hyperbolic disk, the Schwarzschild is 1 over beta squared. And then you integrate over time, and then that gives you a factor of beta, and you end up with a 1 over beta. And here is the same. It's just that the Schwarzschild in this, the integrand of the action in this trumpet geometry, instead of being 1 over beta squared, is b squared over beta squared. And then you integrate over time, and it removes one factor of beta in the denominator. Yeah. Okay. Thank you. Any other question? No? Okay. And to answer the previous question, so I need to do the path integral over this space, and I'm carrying the geodesic because it's the most convenient way to do it, not because it's something special about it. Just picking the simplest way to carry it to perform the path integral. Okay. Now you can compute this wormhole correction to the spectral form factor. So we already saw that the disconnected part decays with time as 1 over t cubed. Naively, if you didn't compute it as a function of time, if you just look at the dependence with S naught, you will think that this is always the leading contribution, because it's the one that grows the faster with S naught. But here we see that when t is very large, then this can be small, arbitrarily small. So then if you look at very late times of order exponential in the entropy, then the disconnected contribution will be small, and then it can compete with this wormhole term. And in particular, the wormhole term, as I said, is independent of S naught. So naively, you would say that it's small. But if you compute it how it depends on time, it actually grows with time. So this already says something that tells you that there is something funny happening when you take times that are exponential in the entropy. The new topologies that you thought were small contribution actually become large at times where you are really probing some aspect from the discreteness of the spectrum, which is when times are of order of the average separation between eigenstates. And again, so this is the two parts of this picture that I showed before. This 1 over this power law decay is this part of the time dependence of the spectral form factor, and this cylinder that gives you something that grows with time is this that is called the ramp, is this linear growth. And of course, this model of pure gravity is too simple to see these complicated fluctuations. Now, this is perhaps the most important point of this lecture and of the results of Sachenko and Stanford. So in what I said before, the cylinder amplitude is not a saddle point in the canonical path integral. Namely, here there is not really any saddle point for B, for example. So here I'm doing a fully off-shell path integral calculation. This is something that is definitely not under control in any model except such simple toy models without propagating degrees of freedom. But something noted in a previous paper by SSS, not the one that I mentioned before, but even a previous one, is that this cylinder is a solution. One can find the classical solution if one works in the microcanonical ensemble. So we can compute the spectral form factor in a theory where instead of fixing the temperature, we fixed energies and we fix a small energy window. So we do some coarse graining over eigenstates. And then when you work in this ensemble, there is something called the double cone, which is an analytic continuation of this wormhole, which actually is a solution. And one way to understand it is to take the two-sided black hole, evolve it in Lorentzian time, and then identify this green line with this red line. Then you end up with this type of wormholes, which is like the one I drew before, but with a complex value of this B parameter in the middle. Sorry. Yeah.
Why do you care about these saddle point things? Because I assume that you fixed the topology and computed that sector exactly, didn't you?
Yeah. Here I'm making a more general comment. Yeah. So what I said, that the thing you just said is valid for JT, but I'm mentioning that if you change slightly the boundary conditions from canonical to fixed energy with some choice of energy window, then one of these off-shell configurations is actually on-shell, so you solves the equations of motion. What I was going to say is that this type of geometries you can write for any theory, actually.
Okay.
So for any theory of gravity, coupled to matter or whatever, if you try to set up the problem to compute the gravitational path integral that computes the spectral form factor, this will be a classical solution that will contribute.
Okay.
For any black hole.
Okay.
Yeah. And this contribution, you can show that first it has zero action because it's a cylinder. There is some subtleties about how to regulate this conical point here, but I think this has been proven that is fine. Then to in order, the action vanishes, but when you compute the one-loop determinants carefully, you see that they grow with time linearly. And this is in a sense more general than what I said before, so here it also grows with time. But in more general black holes, we are definitely don't have the techniques to compute this full function, which is what you are saying perhaps. But still, for any black hole, you can still write down this double cone solution and extract this linear in growth, this growth of the spectral form factor that is linear in time. That's something you can always do. And of course, here the subtlety is that this is not exact anymore, and this contribution will only contribute in a certain regime, for example, at late enough times. Otherwise, this is not the dominant saddle. For example, at short times, it will be the disconnected black hole. And in the end of this lecture, probably the next one, we will see that this linear growth in time behavior of the spectral form factor hints at some random matrix universality of the black hole spectrum. And this is, as I said, is valid at higher dimensions as well. The only difference about the topic of this talk is that I'm going to focus in a toy model where I can actually compute the full function, but in higher dimensions, this ramp is still there. And I think this is something very interesting that we expect to be true and related to the chaotic nature of the black hole spectrum. Is this clear? There's a question there. Yeah.
The spectral form factor is saturated by Plato. Why is that then?
Yeah, that's not captured by this type of geometry. So if you look at very late times, then this probably will not be
then are there
will not be accurate anymore. In JT gravity, we'll see that there are non-perturbative effects that non-perturbative effects in e to the entropy that are responsible for the plateau.
There are
And that one, as far as I know, they don't have a gravity interpretation.
no gravity interpretation.
It's expected to be there from a perspective of random matrix universality. That a chaotic spectrum is expected to have this behavior, but I don't think it's known what the gravity picture is, as opposed to this ramp that has a nice interpretation.
I see. I see. Thank you.
So that's an open question. It would be nice to understand better. Even in JT gravity, it's not understood very well how to get this plateau. It was only understood. Well, the only progress that I know was from last year by Stanford, Krutov. I don't know. Okay, I need to check who would. Shemin Yang. I need to check what the authors were, but where they give some gravity interpretation of some aspects of the plateau, but in general is beyond my reach at least. Any other question? Okay. Okay, but okay, that was just a comment about some aspects of this calculation being more general than the details. But let me go back now to pure JT gravity. Okay. To analyze the more general case with any number of boundaries and wormholes, the first step. So I analyzed some examples. Now I want to move back to the more general case. The way we will do it is to cut out these trumpets of the geometry and divide it, and then glue by including the contributions of each region and then integrating over the internal moduli. And as I said before, one can do this because you first integrate over the dilaton, you have a hyperbolic surface, and every hyperbolic surface has a geodesic homologous to a boundary that one can show. And then you can always cut this more complicated surface into these trumpets and this interior surface with geodesic boundaries. Anyways, when you do this, the general answer takes the following very simple form. So first of all, we have the contributions of the trumpets. This is this C sub T. For example, in this case, it will be a product of the trumpet label 1, 2, 3. Then we need to integrate over the 3 geodesic lengths, B1, B2, and B3. And we also need to integrate over their twists, so that produces this factor of B. And then we need to multiply for a fixed value of B, multiply by the path integral in the interior. And that gives the Bell-Peterson volume that I defined before. It's BG combined. And this is the final answer for the JT path integral on these geometries with non-trivial topologies. Then if you want to compute the full answer, you need to go back and replace each of the value of G in that sum, which, as someone pointed out, it's also not convergent. So this is really better understood perturbatively. Now, we succeeded in writing this partition function as gluing trumpets with Bell-Peterson volumes, but I didn't really tell you how to compute the volumes. I told you that it's difficult even. And there are two methods to compute them that are essentially mastered by Mirzakhani in 2007. The first one is the one that I won't use, but I wanted to mention it. Involves writing the Bell-Peterson volume as an intersection number over the modular space of punctured surfaces. So this is a formula that Mirzakhani showed. The Bell-Peterson volume over surfaces with geodesic boundaries is an integral over this MGN, where now MGN is the modular space with punctures, not geodesic boundaries. And then this omega is the Bell-Peterson form on this space with punctures. The dependence of the boundary appears from adding extra terms that are called psi classes that depend on the boundary length that I'm not going to have time to define. But all I wanted to point out is that once you prove this formula, namely you relate the Bell-Peterson volume with geodesic boundaries to the Bell-Peterson volume with punctures and end up with this formula, then there is something called Witten's topological gravity that essentially computes the integrals over this modular space of products of these psi classes and Bell-Peterson form on these omegas. And you can see this review for a recent account. But okay, this is not this is not the method I will use because it's not very. I will have to introduce what this psi classes are, and that would be too technical. So instead, I'm gonna present the other method that is more geometrical, which is the one Mirzakhani used to show a recursion relation that computes these volumes. And in a sense, what she did was to find a way to deal with this mapping class group. And what you should do, so in general, when you cut a surface by these internal geodesic boundaries, the problem is that there are multiple ways of doing it related by the mapping class group, as I said. But one thing you can do is to go along one boundary, let's say B1, and shoot geodesics perpendicular to the boundary. Then, up to extra cases with measure 0, each of these geodesics will pick a preferred pair of pants in either of these 3 different ways. And by this, what I mean is that you follow the geodesic until it either's, for example, here you follow the geodesic until it hits another boundary BK, and then fattening this geodesic will single out a pair of pants of this form. Or the geodesic can also intersect itself, and when you fatten it, it will pick up a pair of pants with 2 internal boundaries and only one, and the original B1 boundary. So these are essentially the only 3 cases, and geodesics that just move around without intersecting or hitting another boundary have measure 0, and this is a theorem. So all these cases pick up a pair of pants that simplify the surface. In the first case, we end up with a surface with lower genus. In the second case, we end up with, again, surfaces. Oh, this will be, sorry, H1 and H2. So we end up with surfaces with lower genus such that the sum is equal to the original one. And in the third one, we end up with a surface with the same genus but one less boundary. So it always simplifies the geodesics. And this is what allowed her to write the recursion relation. And this is the formula. It's kind of complicated. I just wanted to give you the idea of how the derivation went very briefly. And a very nice derivation to read for a physicist at least for me, is an appendix of a paper by Stanford and Witten. The answer is given by this. So we take the Weil-Peterson volume of the original surface, we multiply by B1, and we multiply by B1 because we want to sum over all these geodesics that we are using to single out pair of pants. And on the right, we integrate over all these choices that this geodesic single out. In the first one, we integrate over the B prime and B double prime are the 2 geodesics that are here. And then we end up with the Weil-Peterson volume of this simpler, with lower genus surface. In the second one, we have a sum over these 2 surfaces. And in the third one, we have the same surface, but one less boundary. And then these functions of the 3 lengths of the pair of pants, B1, B prime, and B double prime, and this T, are essentially functions that can be computed just using hyperbolic geometry. They come from computing, for example, here, then what is the length along the boundary B1, where the geodesic that I shoot will single out this type of geometry. And then that length is D, that you need to include in your integral. But this, I'm showing you just that there are some concrete expressions. But once you did all the rest, then finding these functions is not that complicated. Is there any question about this? If you never saw this before, I don't expect you to follow all the details, but at least just to, I didn't want to not say anything about it, so yeah.
Remind me why you started to compute all this Weil-Peterson. What do you expect after this?
Why did you start with what?
Why did you start to compute the Weil-Peterson volume?
No, because I said that the pure JT path integral on these surfaces with G wormholes and end boundaries is an integral of these trumpets that I know what they are. I have a concrete formula, but then I need these Weil-Peterson volumes to complete the calculation. So what I'm telling you is how to compute this this part of the calculation. Yeah. So to compute the full partition function, I need this as an input to put in this formula. And I don't know what they are.
I'm asking, after you calculate the full partition function, so what do you expect? What kind of information you want to extract?
That we will see. That's what I'm getting at. We will see this duality between pure JT gravity and random matrices. Yeah, that will be the upshot of. Yeah. So far, sometimes in these discussions, the starting point and the thing you want to prove are kind of mixed. So I wanted to separate the calculation in gravity, which is this, and then I'm going to describe what that implies for the boundary theory. But I wanted to first describe how to do the calculation in gravity without jumping ahead. Yeah. But yeah, the final answer will be that this is computed by random matrix integral, and then the continuous spectrum to leading order comes from this integral over random Hamiltonians, and then we will see that. Any other question? Okay, so we have this recursion relation that computes the Weil-Peterson volumes. Using the Weil-Peterson volumes, we can plug them in the previous formula and compute the partition function on any surface we want of pure JT gravity with wormholes. And Mirzakhani also showed that the Weil-Peterson volumes computed from this formula coincide with what you would obtain from this Witten's topological gravity. And then, well, related to also the previous question, Einar and Orantin in 2007, shortly after, realized that this recursion is the same as the loop equations of a one-matrix model in the double scaling limit. And that's what I want to explain in the next slides. And this will be the main non-trivial fact that will lead to the result of SSS. For our purposes for now, this just give a recursion relation after you integrate this over B that determines CGN. And before I move on to the connection with random matrices, let me give you the simplest example of how to compute these Weil-Peterson volumes. Let me just skip this. Yeah. So the simplest case appears perhaps as a one wormhole correction to the black hole partition function. So then if you have the black hole, you have the disk, and then you add a wormhole, so you add a handle to the geodesic boundary, and then the geodesic boundary is coupled to this trumpet, but the trumpet we understand. So I'm just going to focus on this torus with one geodesic boundary. If we apply this to the previous formula to this particular case, then we get that the length of the boundary multiplied by the Weil-Peterson volume of the surface is equal to the integral. So we cut the wormhole here in the middle. This will have some length B prime. And then we integrate over B prime with this particular measure that was derived as part of this Mirzakhani recursion. And if we integrate this measure, this D of B prime, you get this simple answer, B squared plus 4 pi squared over 48. Okay. So this is the answer for the Weil-Peterson volume with one wormhole and one boundary. And then you can go back and combine this with the trumpet, as I said, and compute the one wormhole correction to the partition function. So this is just to illustrate how we use this recursion to do the explicit calculation. Is there any question about it? Okay, something interesting about this result is that, again, similar to what happened with the wormhole, the leading order, so this is the answer from the disk. The disk gives you something that is exponential in the entropy, but it decays at large beta, as 1 over beta to the 3/2. Now, the contribution with one wormhole is suppressed in e to the entropy, is suppressed because of just what the Euler characteristic is for the disk with one wormhole. But you can see that the answer grows with beta. So if you go at very low temperatures, exponential in the entropy, at some point, this result will not be dominant, or it will be so small that it can compete with these wormhole effects. And again, this is the range in which you expect at least some indications of the discreteness of the spectrum to appear. And one can even find the behavior for at very large beta or low temperatures for any number of handles G. And then you see that as you add more and more handles, the divergence with large beta is even bigger and bigger. So the more you go at lower and lower temperatures, this perturbative expansion breaks down. So, okay, so that was the solution for pure JT gravity. And now I want to move on to the interpretation, how I'm going to interpret this result that I mentioned. Yeah. This? Yeah, this one is resummable, yeah. But I only wrote it in some limit. I think the problem is that there are corrections that grow slower with beta that can diverge faster in terms of the genus. So corrections that are lower with beta can grow as 2g factorial, and then those are the ones that are asymptotic. So this is just part of the full result. I mean, you shouldn't take this as a indication that somehow I can compute the yeah, it's a distraction that this is finite. It's usually the actual sum is diversion. Yeah. Any other question? Okay. Okay. Well, the first comment to make is that so far, based on what I told you, it's not clear what makes the spectrum discrete at all. But we will see in what sense it's discrete in the when I describe the random matrix dual. And actually, it will not be discrete. It will be an average over Hamiltonians with this discrete spectrum, and then this continuity will appear just from this average. Yeah. Yeah. It's meaningful if you're not at too low temperatures. Then it depends what you compute. There are some quantities that are more sensitive to non-perturbative effects in this genus expansion, and some quantities that are not. So it's well, for example, in this spectrum form factor, this slope and the ramp are kind of perturbatively well defined. You can understand them from the disk and the wormhole. But then if you go to such late times that you're trying to see this plateau, which is the real time scale at which you would see the discreteness, then this is not understood as anything perturbative in the genus expansion. Then you lose the geometric interpretation, which is what someone was asking also before. Yeah. Is it possible to what? Sorry. Is it possible to show it? No, that's the problem. It's very difficult. Instead, what I will do is to show you perturbatively that the theory is dual to a matrix integral. And then the matrix integral is what tells you that there should be a plateau there. Yeah. But that's the problem I was mentioning before when someone was asking. There's an open problem of understanding this plateau from gravity without talking about the dual random matrix or anything like that. Somehow, it would be nice to have a model, some gravity saddle. It's probably too hopeful, but something like this double cone that it's always a solution that you can write down easily and give you this plateau. But that's I don't know how to do that. Yeah, that's an open problem. And yeah, there was some progress last year, but I'm not gonna have time to discuss it. But I think it's still an open question. Yeah. Anything else? Okay. Um, yeah. So the second problem, well, the first is that, yeah, related to what we were discussing just now, it's not clear how the solution makes the spectrum discrete yet. I just showed some features that are common to the spectral form factor of a chaotic spectrum that is discrete. And the second problem is that this wormhole spoiled the assumption that the black hole is dual to a single quantum system. It's also what Seok was asking. So there is nothing telling you that the gravitational path integral with two boundaries is the product of individual gravitational path integrals with one boundary. This is definitely not true in the models I studied so far, in particular because of this wormhole. And I think it's just a problem we have to live with. And I think what came out of these discussions in the past years is, if you want to impose factorization, you should not remove these wormholes that would not be, you would run into other issues. Instead, you have to include these wormholes, and if you want a theory that is dual to a single system, you have to add other stuff that would somehow remove the wormholes in quantities that are bad, like this, but keep them in quantities that are good. For example, this ramp in the spectral form factor. But understanding how to solve this is called the factorization problem. Is really an open question. Well, there are toy models, but understanding a general mechanism or the way we expect it to work in examples from string theory is not really understood. Okay, this is what. So yeah, so string theory suggests that, maybe to mention, so this is, I think this was first raised by Witten and Yao around 20 years ago. In the examples of string theory that we know, the factorization is restored, and we want to understand how that works. Instead, for this model of pure JT gravity, the answer is that it's just a theory that is so simple that it doesn't really know how to distinguish the different quantum systems, and it's actually, we will see that it's dual to an ensemble of quantum theories. So the upshot of what I will describe next is, or what is this holographic dual of this pure JT black hole proposed by SSS. So the answer is the following. You take the black hole Hilbert space of dimension of order e to the entropy. And a quantum system is described by a Hamiltonian acting on this Hilbert space. And the dual of JT gravity is actually an ensemble average, an integral over this random Hamiltonian with a specific probability distribution. So in gravity, you compute the path integral with multiple boundaries. And in the dual quantum system, you compute the partition function for a given Hamiltonian, and you take the product. And then at the end, you average over this Hamiltonian. And that's where this lack of factorization comes about. In particular, this probability distribution for the Hamiltonians is a very concrete function that they found, and is essentially related to the leading order density of states in the large S0 limit. We will see that in the next slides. What SSS did is to show this equality here to all orders in this e to the S0 expansion. And this is what I want to describe next. But another subtlety is that this matrix integral is in the double scaling limit, which is, I will explain also next, related to how well, these two statements come together. And what that means is that we will take a limit where actually one takes L to infinity. But we will see that later. But very broadly, you can think of the duality in this way. So the gravity path integral is some average over Hamiltonians. Is there any question about this? Yes, you can change the dilaton potential of the theory. So you can solve theories with different dilaton potentials, and then that will. So you basically, if you talk about pure dilaton gravity, you have one function worth of theories given by this U of I, and then you have one function worth of this matrix model. So they are in one-to-one. Yeah, I might mention in maybe near the end.
Question for finite L, this is not on duality.
It's not the what?
Duality is not correct for finite here.
No, you have to take L to infinity, but I will explain that. That's what I will explain. Now.
Thank you.
Yeah. Yeah, there's a question there.
When you say if you want to resolve the factorization in the gravity side, you said that you should add some extra contributions. Is that some other geometries in the gravity side?
Yes, but I don't think they're understood very well. Like there is this proposal of half wormholes of a couple of years ago. There are proposals with something called eigenbrains. There are a lot of proposals. I think the difficult one is to identify which one is the physical one that happens in more realistic models. But yeah, you essentially keep the wormhole. You don't want to remove the wormhole, or that gives different problems. You keep the wormhole, but then you add something else. That
add something else to total partition, total spectral form factor be factorized.
So you add something else to the wormhole in the sense that you are not doing pure JD gravity anymore. You have to add extra objects in the theory, either have wormholes or some type of brains. Yeah, that's the
Okay, thank you.
So the theory is not pure JD gravity anymore. Yeah. So there are a lot of models about how to resolve this factorization problem, and again, the question is what is the general lesson that comes out of the models, and what, Okay, so I will try to explain what the right-hand side. So far I explained the left-hand side, and now I will move on to what the right-hand side means, and then how to show this equality. So I will start very slow with a short review of what matrix integrals are. So it will take. Perhaps I won't show it until tomorrow, the next lecture, that this equality. I will, in the remainder of this lecture, I will just tell you what the right-hand side is. But okay, so start with an integral over L by L matrices. At this point, L is finite. We will take L to infinity later. And the integral at large but finite L has a Toft expansion. So if we try to compute such an integral over H of this product of partition functions, then this has a perturbative in large L expansion, which can be understood as topological in the sense that you can think of these Feynman diagrams of these matrix integrals as discretizing a two-dimensional surface. And then this genus, what it's counting is the genus of this discretized two-dimensional surface. So if you add handles to this Feynman diagram, then that will suppress it by an extra factor of 1 over L squared, etc., such that to leading order you only have planar diagrams. And in the matrix integral, this is imposed by the fact that we assume that the probability distribution is given by e to the minus L trace of some function of H. Here, this function of H is of order 1, doesn't grow with L, but this prefactor of L is the thing that is responsible for this topological expansion, and it imposes the Toff limit. Okay, and to leading order in this genus expansion, large L, the potential V of H specifies some eigenvalue density of states. So this rho of E is the density of states of eigenvalues. And if you tell me what V of H is, then I can tell you what the leading order this density of states is. There is a one-to-one between them. This density of states is of order L. You just look if G is 0 and N is 1, you get L to the power 1. And in general, not always, but in general, it has a single cut. Sometimes it can have multiple cuts. But importantly, it always has a finite extension that here I call A. So if you give me some V of H, then the support of this leading order density of states will be finite. We will have some complicated function that depends on V of H. And this will describe some average description of the spectrum in this large L limit. Let me give you a sketch of the derivation. So we start with computing the matrix integral without insertions, just for simplicity. So I'm just computing the integral over h of this P of h. We will insert these partition functions later. And the way this is done is that you decompose the matrix H in this eigenvalues lambda and this change of coordinates U, given by this unitary matrix U. And we can integrate out this matrix U and reduce the integral over H to an integral over its eigenvalues. And I don't know, I will assume that everyone saw this at some point. If you didn't, you can ask me afterwards. But if you the upshot is that the integral over these eigenvalues that I'm calling E, and I call them E because I want to give the interpretation of this matrix as a Hamiltonian, is given by just a flat measure. Then it's given by replacing this diagonal matrix into the this potential V of H. And then there is an extra Jacobian that is called the van der Monde determinant, which is a product of all the energy differences squared. And this comes from integrating out this matrix U. So then we can write the matrix integral as an integral over L eigenvalues with an effective potential E that comes from this original potential and also from this van der Monde determinant. So this is the formula. We have this V of E and the van der Monde. Okay. The first thing I would try to do is to find the saddle point of the spectrum. What are the values EI for I from 1 to L that extremize the effective potential? Now, it happens to be that this is not the right way to think about this problem because, well, naively then you could say, okay, then I have my most likely spectrum and then I can just work with that concrete most likely spectrum and compute things with that theory. But that doesn't work. What happens is that when you look at such a saddle point, the fluctuations around the saddle point are larger than the average level spacing. So the fluctuations around the saddle point is of order 1 over square root L. This just comes from looking at Gaussian fluctuations of the effective potential around the saddle point. But the average level spacing in this regime where we expect to have one cut with a finite extent, the average spacing of the eigenvalues is of order 1 over L. So the fact that this spacing of eigenvalues is much smaller than the fluctuation means that it's not really correct to think that we have a saddle point for the spectrum. Instead, the way to think about it that I mentioned already before is to think that we have a continuous variable that is the density of states, and the saddle point is not on the individual values of E, but it's in this function rho of E that you should try to do a saddle point in the large L limit. And this has a good, well, properly normalized, it has a good large L limit. Is there any question about this? Okay. So then we want to rewrite the matrix integral as an integral over this density of states rho of E. Then my effective potential is a functional of rho of E. And then you want to extremize with respect to this function rho of E itself. In terms of this rho of E, the effective potential has this form. So this is the trace of B of H that I wrote before, just written in terms of this continuous variable. This is the van der Monde determinant, where now I have two integrals. Before I had two sums. Now I had two integrals with the respective density of states. And then you can think that you can add a Lagrange multiplier to impose the normalization that the total number of eigenvalues is equal to L. So this you need to add by hand, and mu is the Lagrange multiplier. And now you can use that. You can look at the saddle point equations of this effective potential instead. And then we should study fluctuations around the large L limit of this rho of E, and not of the individual energy levels. And then finally to compute the partition function, we simply compute for a given density of states, we compute these traces by integrating over energies using this leading order average density of states and inserting e to the minus beta E. And similarly with the spectral form factor. Now we insert two rows, two Boltzmann factors, but now we need the average value of the product, which can have
disconnected pieces, but also connected contributions to it. And you can roughly think of this as some kind of mean field approach, which is the conceptually correct way to derive rigorously the loop equations, which I will mention next. Okay, so let me mention an example. So, so the classical equations that come from varying rho, after massaging them, they can be written in the following way. So the derivative of the potential with respect to the eigenvalue is equal to this integral of the density of states. This is called the right-hand side is called the resolvent. And this is a very complicated functional equation that can be resolved with the resolvent method. And for this, you can see any random matrix theory review, or for a discussion more closely related to the topic of the lecture, you can look at Stanford Witten. I'm not going to describe how to do it. This I will leave as an exercise, I guess. But for example, in the Gaussian ensemble, where V of H is quadratic in H, here I introduce the parameter A, just for concreteness. Then the solution of this complicated equation is the famous Wigner semicircle law. So the density of states to leading order is the square root of E times A minus E up to some prefactor. So here you can see that the density of states to leading order is this semicircle that goes from 0 to A. And here I pick this funny potential such that it has this property that goes from 0 to A. So again, I'm not deriving this, but this is the result that one gets. Now, how much time do you have? Probably done, right? Huh? It's over. Okay, great. So in the next lecture, we will define the double scaling limit and continue with this and finish making the relation with pure JT gravity. So that's all. Thank you.
All right, it's time for questions.
Maybe can you motivate a bit more on why JT should be related to this random matrix theory at all? You showed us a formula and it's shown up to all of the expansion, but maybe could there be some more intuitive way of understanding it?
Well, intuitively, you could say that you are doing pure gravity. So, in a sense, you are doing the roughest theory of gravity you could do without any kind of object or anything there. So then you naively could intuitively expect that to be some kind of averaging, because you don't have any information that selects one Hamiltonian compared to another. If you have matter, then that's different, because then you can give more. There are more things you can compute that could, in principle, single out particular theory. So you could expect that the less you put into the gravity theory, the more random, the more undetermined the dual is. That's intuitively the one way to think about it. More concretely, again, you can compute the path integral and then you see it doesn't factorize. So you either, I don't know, say, okay, it doesn't work, I'm done. Or this idea of the dual being some average over theories is a way to make it consistent with this factorization.
Also, I mean, two-dimensional gravity from old days has been related to matrix models. Is it somehow related to that, or is it completely new?
Yeah, this is actually. Yeah, I didn't want to say that because maybe for some people maybe it's not intuitive if they're not familiar with that. But yeah, pure JT gravity is a limit of the minimal string. The minimal string is a theory where you couple a minimal model to worldsheet to the gravity. It's a special case of the non-critical string.
But I guess it's much older. I mean, I'm not sure correct, but it's two-dimensional gravity via triangularizations and so on.
No, that's what I'm talking about. Yeah.
Yeah.
That's the minimal string. Yeah.
Oh yeah. So this is related to that, do you think?
Yeah. So pure JT is a limit of the minimal string.
Okay, I see.
Yeah,
I see.
And the minimal string is dual to. If you pick the 2, p minimal model to couple it to gravity, then it's dual to a one matrix. It was conjecture in the old days that it's dual to a one matrix model, and the interpretation was that it triangulates the surface. And JT gravity is actually the large P limit of the 2, P minimal string.
Okay.
If you pick more general minimal models, then it's dual to multi-matrix integrals, and that one doesn't have a JT-like interpretation as far as I know. But just a last comment, there is a very different interpretation between the matrix here and the matrix in the old literature, which is that here the matrix is not triangulating the space, the matrix is a Hamiltonian, is the dual Hamiltonian. So yeah, in some sense, this is closer to the original Wigner motivation to introduce random matrix, where you have a spectrum that is very complicated, and then you somehow model it by saying that the spectrum is random. One way to think about it is that example that I mentioned of the double cone of random matrix universality, where even in theories that are not dual to ensembles, there are certain configurations that should give you some random matrix universality because of the chaotic nature of the black hole spectrum. Yeah, so the interpretation is very different, but it is a limit of those old dualities. Yep.
Actually, I have two questions. One is related to that first question about the C=1 matrix model, where this original singular sector, there is no black hole.
Sorry, I mentioned the minima string. That's a different.
Yeah, okay.
Yeah,
then
yeah.
the difference. Okay. Then the second question is here we usually obtain this kind of two-dimensional model from the higher dimensional extremal black hole. So you talk about the many other non-perturbative effect and
Yeah.
so on. Then how can you interpret that such kind of like a wormhole or this kind of new geometry in the higher dimensional point of view?
Yeah, well, partly that's why I wanted to mention this double cone geometry, because it's, again, in higher dimensions you don't really have access to such small contributions, because that's why logically I wanted to separate the first two lectures from the last two, because this is really a toy model where I can compute things exactly, which is not the case in general. But that's the nice thing about this double cone, that even though even though in a higher dimensional theory that might be dual not to an average but to a specific chaotic Hamiltonian, still have some features of this random matrix behavior. But specifically to what you were asking, this procedure of creating the double cone out of the two-sided black hole can be done for any black hole. You can start with a higher dimensional two-sided black hole, and then do this Lorentzian evolution, identify them, and then that will be your double cone that computes the linear in T behavior of the spectral form factor. So you can just do it with the near extreme higher dimensional black hole. Then it will be a double cone that looks like something else far away, and then very close to the tip, it will look like the double cone of JT gravity. Yeah. Is that what you were asking? Okay.
Okay, so compared with the old minimal model, minimal string.
Yeah.
Here you have a constraint of R is scalar coverage is -2.
Mm-hmm.
So how that constraint is affecting, I mean, in the difference in the random matrix model?
Yeah, so that's a good question. We are not imposing that in the random matrix model. But there is one way in which you can think about it, which is that, so as I said, maybe I should write there. The JT is a limit of the 2, P minimal string when P is large. Now, you can ask what is the coupling of the Liouville theory. So the minimal model coupled to gravity becomes the minimal model coupled to Liouville gravity. And then you can ask what is the coupling of this Liouville gravity when you take large P. And this Liouville gravity actually becomes weakly coupled at large P. But the question of motion of Liouville is that it localizes to hyperbolic metrics. So in a way that is not very well understood, when you take the matrix potential for JT gravity for the 2, P string and you take large P, that should localize to hyperbolic surfaces, triangulation of hyperbolic surfaces. But that's not understood from very well. It's understood in the continuum limit, just the fact that Liouville becomes JT, but
So
not from the discretization.
basically, you assume that just both minimal string and the JT gravity both are dual to the random matrix model?
Well, for JT gravity, I can do even better because I can prove it, or SSS proved it perturbatively in the topological expansion. In the minimal string, yeah, sorry, I guess I divided the lecture in two. I will describe how to derive it in the next lecture, but okay. But in the minimal string, there is not really any derivation, right? It's more like a conjecture and some arguments based on the triangulation. So I think it would be nice. I think that would be an interesting open problem to find a way using string theory techniques to prove that duality, imitating what people did for JT. For example, in JT, the way you sought to solve it was to find a recursion relation for higher genus corrections. In string theory, you can ask, is there a recursion relation that computes higher genus amplitudes in string theory? That you can ask even in general in the critical string or whatever. And this kind of, at least for the minimal string, indicates that such a recursion relation should exist, but I don't think anyone knows how to derive it. I think it would be nice. That would prove the old dualities as well. Yeah.
Thank you.
Yeah.
There's a question from online audience. So he's asking, in your second lecture, you mentioned about 2-point functions with bulk matter. Can you clarify the validity of the computation? He's asking within the disk geometry and what could be missing. Is this perturbative exact? He's especially concerning about the bulk matter Hilbert series, which is infinite dimensional, seems missing in the treatment.
Yeah, so I said in the beginning of this lecture that as opposed to higher dimensional gravity, JT gravity has two coupling constants. That's one way to think about it. One coupling constant is S naught, that, and in the first two lectures we took S naught to be very large, infinite, let's say. And then we restrict to the disk. And moreover, not only the disk, but also by some examples from the way JT gravity arises from near extremal black holes, also ignoring interactions between the matter and the dilaton. That there are complicated interactions that would be suppressed in S naught that we neglected. So okay, S naught was taken to be strictly infinite or very, very large. But what we did in the first two lectures was to solve it exactly in the other coupling constant, which is this dimension full parameter C. And in that coupling constant, you can solve it exactly. And that's what we did in the first two lectures. But because it only works for large S naught, it doesn't see anything about the discreteness of the spectrum. So the two things are not inconsistent. It's just the fact that now there are really two parameters in this model. In principle, if you look at higher dimensional black holes, both parameters are of order 1 over g Newton. But the special thing of JT gravity that in the first two lectures is that the coupling of this perturbative boundary graviton, this C, even if it's of order 1 over g Newton, or the coupling 1 over C proportional to g Newton, the fact that it's dimensionful and it gets multiplied by the temperature means that even if S naught is large, you can always go to low enough temperatures such that that mode is strongly coupled. And then that allows you to study those two effects separately. Yeah.
Okay, sorry.
Yeah.
Maybe a follow-up question. You just said that the matrix model here, the proposed matrix model, is different from the original, like this triangulate the surface and there is a resulting matrix model. The two are different, right? If I understand correctly, like for a given triangulate the surface, there is a matrix model, and we can read out the geometric data of the origin of the surface. So is there any geometric picture for this proposed matrix model here?
Well, first of all, we want to emphasize not that perspective of the matrix as creating a geometry, but we want to interpret the matrix as a Hamiltonian. So in that sense, I don't want to talk about that interpretation. That's not really the one I want to focus on. But if you're asking the interpretation, then you can just look at the old literature on the minimal string and the interpretation of the 2, P at large P. So usually you interpret the way they wanted to say that you're adding matter is that you add higher powers of the matrix in the potential, And then somehow these different type of vertices can model kind of matter moving in the geometry, and that's the 2,p minimal model. Yeah, but I see those more as a, not as a completely precise statement, but more like a hint,
So
perhaps.
if I look at this old literature from string theory, for example, for a given matrix model with a given, let's say, potential way, and you can figure out what is the curvature, for example, -2, -3 stuff, or something.
Well, usually the curvature is not fixed.
Oh.
When you matrix models that triangulate surfaces don't have a fixed curvature. I was mentioning as an answer to the previous question that there is some evidence that happens for the a large P limit of the 2,p string, but in general that's not something that the way a matrix model triangulates. At least not this matrix model. There's something called dually weighted graphs or something like that. Was introduced by Kazakov, Staudacher, and I don't remember the third author. But they are matrix models with a more general probability distributions that can fix locally the curvature. But the matrix model integral does not have this form. So here I made an assumption about the matrix integral that it has the form e to the trace of function of the matrix. That's an assumption. And if you allow more general integrals, then you can do other things. But this integral that I studied doesn't fix the curvature.
I see. Okay. So if you, so is there any way or any trying to figure out, for example, study string theory to give you both the geometry and the matrix interpretation, or that's sort of an inverse question I just asked.
I don't know. That's kind of the indication of what should happen at large P, but it wasn't done. Yeah, ideally, perhaps you would want a model where you impose that the curvature is constant, and then you take the continuum limit, and you get JT. That wasn't done.
I see.
Only as a limit of the minimal string.
Yeah, thank you very much.
More questions? From Zoom? No? Okay, if not, let's thank the speaker again. There is an announcement.
All right, so you guys saw the discussion session, something mysterious. I don't know that, what it is. Originally, we are thinking about some Gong show with people from outside, but I realized that that's not a good idea. So I just left as it is. So today, roughly, I guess everybody's probably tired with these wonderful talks. You want to have some break. But 30 minutes later, I think 4:15 pizza will arrive. I asked them to bring the pizza and drink early. And then during that process, again, we can do some sort of poster type of thing. People. And then also, hopefully, lecturers will be around, so you can ask questions informally. And that seems to be a reasonable thing to do. And then maybe tomorrow afternoon or day after tomorrow, we clean up the poster. So that's what I would suggest. So let's have a break for 30 minutes, then around 4 we get together, and then pizza will arrive and the people talk to each other. And I guess that's what we do. All right, thank you.